Raim, where is Fatima? She's not online.
She's here. Let me ask her to be online.
Accendete Poi accendi la tua macchina. Non ti si vede però. Wang Yu, good morning, good afternoon. Where is Liang Li? Liang Li. Liang Li. Where is Liang Li? Who is Alcides Garat?
Good morning, Professor Ruffini. I am Alcides Garat. I am here in Uruguay, South America.
Yes. Good. You are following our work?
Yes, I am.
Where are you?
In Uruguay. We met at Gramado in Brazil 5 years ago.
Yes, very good, very good. Excellent. Carlo, ci sei? Yerlan, good to see you. We have progressed. Carlo, metti la tua camera. Ok.
Salve. Ciao Lorenzo.
Sì, sto riflettendo anche alla luce di discussioni locali. Dobbiamo assolutamente non perdere tempo sulla roba. Siamo d'accordo sul raffinare il wording. Ok. Maybe we start. Although Massimo non c'è. Io credo che la cosa da fare, ci ho riflettuto un po', la cosa da fare è, il caso scientifico è chiarissimo, è non fare una cosa piccola, ma fare qualcosa che sia della dovuta dimensione di area collettiva, semplice su questo, e poi vedremo adesso le cose da misurare, e le cose da misurare le vedremo oggi, e dopodiché fare la missione ottimale che sia decisamente 90% più potente di quella attuale. Esatto, e puntare su essere flag di OHB in Germania.
Possiamo sfruttare questa connessione che abbiamo da sotto e da sopra.
Sì, quella di sopra.
Ma anche da sotto intanto.
Sì, ma bisogna educarlo.
Sì.
Perché?
No, da sotto di lui, cioè quelli con cui ho collaborato io,
sì,
che spingono.
Sì,
però
in quello fra i due, fra il capo e l'erca, bisogna educarlo. Perché io ho educato il padrone.
Magari posso cominciare a parlare quelli da sotto.
Sì, che gli parla subito, oggi pomeriggio. Oggi pomeriggio. Anzi, Elisabetta, se ci sei in linea, fammi avere il nome della persona dell'OHB, portamele su, le foto anche.
Ok, OHB Italia o Germania?
Italia.
Ok.
Sai che l'OHB sta facendo il framework del telescopio nella Terra. Il prossimo GK lo fanno loro. sarà pronto fra 10 anni. Io col Presidente ho detto, voi mi seguite, io nei prossimi 10 anni vi farò il programma per il telescopio di Atacama.
Sì, ma lo spiro, esatto, anche in ESA.
Molto, sì.
So, siccome il momento
Sì.
è giusto, se la farò proprio spinta.
Sì. Va bene. I think it's better we start, no matter if everybody's here or not. May I have, okay, the usual slides that we usually show? The one where you have on the left the binary, and on the right everything else. Because I think this is a fundamental point which we were sì. Va bene? Yes. Tutto schermo. Ok. I would like to say a few things as an introduction. And you learn not only from the success, but also we learn also from the mistakes. And of course, not if the mistakes are too big, but still some mistakes are important in order to change one's opinion. And it was at the end of the fantastic adventure that we had following the X-ray observation of the Uhuru and the Einstein telescopes that we reach with Riccardo and with Riccardo Giacconi and Herb Gursky, the understanding, complete understanding, with only one exception of binary X-ray sources. Paradoxically, the exception we have in understanding the entire system, Centaurus X3, Hercules X1, and so forth, paradoxically was the one which gave me personally the greatest success, namely the discovery of the black hole in Cygnus X1. But what is still today, we do not understand precisely the role of Cygnus X1. Of course, the data have been refined. We have seen at the last MG16 the new data of Cygnus X1. The mass has increased of roughly 20%, if I understand correctly, the mass estimate. But still, we don't understand how this system was formed. Therefore, with only that exception, I think we had reached a profound understanding of all binary X-ray sources, and the book we finally published with Riccardo deserve the right reading and attention. A big success story. But at a lecture I had in a university in the United States, somebody asked a question: what happens to a binary X-ray sources? And then I said, oh yes, of course, they will evolve. But it will take 10 to the 8 years to wait to study evolution of such a system. And today, we don't have such amount of time, and I laugh. This was one of my bigger mistakes. Because, of course, this was a great opportunity. But the key point was that we were looking only to galactic sources. And gamma ray burst they were not understood. And it was not after the X-ray, but the gamma and the X-ray mission of Beto-Sachs that we learned about the nature, the energy of GRBs. Never a statement was so wrong as to say we have to wait 10 to 8 years. And the reason is simple. The binary X-ray sources we had of the order of a few years. GRB we had once per day. It was known. But it was not until we understood the opportunity of GRB to be extragalactic that the system of a GRB, originating the GRB, was observable in all the stars and all the galaxy in the universe. And therefore we were really looking at the end of life of a binary X-ray sources. But the key difference is that the end of the life of a binary X-ray source, which you see there on the left, okay? The end of life of a binary X-ray sources is much more energetic than we expected. Therefore, is visible in all the 10 to the 9 galaxies in the universe. La fine. The end was that is visible in 10 to the 9 galaxy, visible always, which meant you have to take that factor of the observation in the galaxy and multiply by 10 to the 9, and therefore instead of being 1 or 2 per year, it becomes 1 or 2 per day. This was a fantastic thing, and we came back to this. But we came back slowly. I still remember being in Nice with the people at the observatory who had studied in great detail Eta Carinae. And Eta Carinae is precisely a system of that kind over there, 2 very massive stars of roughly 100 solar masses. And Eta Carine, again at the university, at the observatory in Nice, this researcher had found out that also Eta Carina was in binary. And therefore, that this was really the starting point of the entire game. This is the crucial point. And now we know, first of all, that the majority of stars of 100 solar masses are indeed in binaries, like Eta Carina, and possibly the totality of them are in binaries, the very massive star. And the more massive star, the more massive of the two, undergoes gravitational collapse and form a neutron star. And therefore we have a second era in which you are left with the less massive star as a companion to a neutron star, and starting the binary X-ray source phenomena like a SNX3. Not Cygnus X1, unfortunately, but Hercules X1 and all the other one. Therefore, the novelty is that when a system like SNX3 evolves, then we are exactly on the next layer in which the evolution of the massive star, companion of the neutron star in SNX3, gravitational collapse undergoes a supernova, and this supernova accretes on the previous neutron star. And that is, forse devi scendere di un pochettino l'immagine, and that is the beginning of the process of the binary-driven hypernova. What happened? You're missing the bottom slides. Eh?
I don't know why I see here this dark screen on the...
Gabriele, cosa succede? Che no? Ci ha tagliato i piedi.
Io vedo un quadro verde, che non so se la risoluzione massima.
Okay. And then we have this supernova undergoing on a companion neutron star. And this is the starting point of what we call the binary-driven hypernova. I hope this is clear. Is clear? No doubt. Okay? No objection. There is something which is trivial, very trivial, but hard to have people understanding. We know that in a supernova, you create a neutron star. We know that from the Cam Nebula. Therefore, these two, the first neutron star, the companion neutron star, came from the first supernova. But the second supernova, as a supernova, must create a new neutron star. And therefore, there was no better choice of calling, to distinguish from the other neutron star of the previous supernova, to call this a new neutron star. And with the effort to convince the editor to accept the definition of new neutron star, because new in Greek means new in Greek means new, and we decide to call new neutron star And this, instead of simplifying the matter, has made the matter more complicated because people start to say, oh, new like neutrino. No, it's simply new because for the people knowing Greek, new is new. And therefore you can interpret new as novel. But I invented a new neutron star to simplify, and instead it became very arduous for people to understand. Maybe we have to change the name, but now it's so much common. Okay, therefore the system is very simple. The system is the supernova. Laura Becerra has taught us how to describe the system. The new neutron star, by definition, is at the center of the new supernova, and the accretion on the new neutron star originate, and this was one of the major points of our model, originate the X-ray afterglow. Namely, the accretion of the ejecta of the supernova on the new neutron star originate the X-ray afterglow. Therefore, the characteristic of BDHN model is that the X-ray afterglow are nothing else on the left, on the bottom, than the accretion on the new neutron star of the supernova ejecta. Therefore, this is the first fundamental assumption. X-ray afterglow means accretion on the new neutron star. And we can consider the spin of this. Vice versa, the accretion onto the companion neutron star accretes on the mass of the companion neutron star, and there are two possibilities. Either that mass increase to the critical mass value and form a black hole, or it stopped before in a second massive neutron star. The first one we define because they are by far the most powerful, the BDHN1, the binary-driven hypernova number 1, and the second one, the binary-driven hypernova 2, which are composed on a new neutron star, on two neutron stars, the new neutron star and the old neutron star with accretion more massive than before. We have another diagram somewhere in which we speak about the next layer. From this binary neutron star, the new neutron star and the companion more massive, the system evolves toward short GRB, and we should show that one if you don't mind, but later on. And therefore, the very important statement is that there is all this branch going to a black hole neutron star binary, to two neutron star binary, and then there is the last evolution, the two neutron star binary going into a black hole. This characterizes the short GRB, and or otherwise the two neutron stars going to a more massive neutron star, and these are the X-ray flash. Therefore, in conclusion, we can see the entire family. The beginning is one, standard, two massive stars of 100 solar masses. But then, through an evolution which is slow, and each step characterized by a different episode. The first one, the first supernova, the binary X-ray sources, the second supernova, the accretion, the birth of the afterglow of the black hole and of the JEV, and finally the short GRBs are part of a system very, very complex of what? Of a system of very independent process. Each process is independent from the other one, independent. Therefore, each one needs its own description. And the only contact between this independent process are the initial and final boundary condition. Every episode is linked through the boundary condition to a further episode. And even within one episode, you have many independent episodes, again linked temporarily by boundary condition. And therefore, the richness of the evolution of two very massive binary stars consists in this richness of process, which goes from the building of heavy element to observation of new process, to supernova and so forth. And now finally we are in the condition to describe in a first approximation all the details of this process. Of course, this point of view, rich of so many independent episodes, all of them which have their own scientific authoritative status, differs from another approach which has been followed for some time by Thorne and this Misner, Thorne and this group, that very massive stars just produce black holes, and then the black holes emit gravitational waves and form a larger black hole. This history is completely different. It's full of science. And to consider that possibility just shortcut the entire history of the universe. And so much so, and I would like to start to go in depth in some of this description. The only point I would like to make is that also the other difference is that in each transition, there is the possibility to create a black hole. But very interesting, black holes can either be formed in an evolution of a BDHN1 or in the evolution of a binary system. In both cases, the transition of accretion leading to a black hole is smooth, and there is no a large or significant emission of gravitational waves. This applies both in the case of BDHN1 and in the merging of short GRBs, where the testimony of this smoothness is represented by the fact that the short gamma ray burst give origin to jet emission. Jet emission implies inner engine, the inner engine active following Rueda and my work, the inner engine and the work of also some other collaborators, including Raim, and that transition is smooth due to the fact that the black hole is emitting immediately jet radiation, implying that there is no binary neutron star going to a black hole, but a binary neutron star, magnetized neutron star, creating an inner engine with a Kerr black hole associated with a magnetic field which originates the jet radiation. This result is the key one of the key points we will present here. È chiaro? That's it. I will stop at this point to let all the collaborators work. Maybe also ask Amati, Lorenzo to give us a general introduction of the instrumental point of view. But let me take that tomorrow we will, at the end of the presentation, we will indicate that indeed one of the key tools to understand gamma ray burst is precisely the Amati relation. We knew that for a long time that was significant, but we have not understood the physics underlying, which we will present tomorrow. Ok? Vediamo se ci sono. Lorenzo Amati and following by all. Let's see if there are questions.
Remo, thank you so much for this very useful overview. Just a more specific question. My understanding, of course, is that in this scenario, as you said, the X-ray afterglow emission, so the early afterglow, the flares, the plateau. So your scenario, the scenario developed by ICRANET and your team, explains very well things that cannot be accommodated in the standard scenario, where you cannot explain the long duration of the plateau, the flares. So this engine based only on black hole and possibly evidence of prolonged activities that only neutron star engine can explain. I was wondering if for the subclass of short GRBs with soft extended emission, of course, this should fit qualitatively very well the idea that the soft X-ray emission, the extended emission, which is very different from, because we have the short spike, you know, hard spectrum and so on, and you have this long soft X-ray emission. So this may be already attributed to the neutron star, the newly born neutron star accreting matter, so accreting from the remnant of the supernova. Is this correct? Or is something different?
No,
okay.
No,
So,
no.
Okay.
No. The key point is we need that diagram of the short at the end. The key point is the binary, and first of all, I thank you for clearly indicating a fundamental distance. The fundamental distance from the traditional picture is who is just alive. From the traditional picture is very fundamental, is that the traditional picture use a very inefficient process, namely by gravity, but we will have time to see this, by gravity, using gravity as an acceleration, using my circular orbit of 1969 developed with which you find in Landau-Lifshitz. People will try to use the gravitational binding energy of particles to create a jet or very high gamma expansion. The idea is we have written finally this. The idea is simply not correct, but the idea is trivial in a certain sense. You have a jet, ultra-relativistic, okay, interacts with plasma, and then lose its kinetic energy by generating X-ray and so forth. Okay? This mechanism, first the production by gravity, of accelerating the shock wave. Second, the interaction of the shock wave with the interstellar medium kinetic radiation is not efficient.
Which is a main issue, well-known main issue in this no? Efficiency.
It's not efficient enough. What is our solution is that the acceleration occurs on the source. What do you mean on the source? Either on the black hole surface, okay? And this electromagnetic has no gravity. One day I was in Stanford and I wrote a message to our friend in there who is thought to be one of the main thinkers of the process, which is Blanford. And I said, I wrote a note to you, we should have courage, both of us, you to forget about the Blanford mechanism, and I to forget the last stable orbit. We have to forget, because the process does not work gravitationally, it works electrodynamically. You agree on this, Olga? It works electrodynamically. I hope everybody follow this part. It works electrodynamically, has nothing to do with gravity. The first big revolution. The second revolution comes about the shock. The shock comes at the end. They have nothing to do with BDHM. They though we went in the trap, I was just reading yesterday on a trap on a paper which fortunately was not sent final publication. It was correct and put that the attempt to have a short by BDHM doesn't work. The short comes from binary neutron star. And now the binary neutron star comes from neutron star with magnetic field. And this magnetic field works both in the case that you have a binary neutron star coalescing to a more massive neutron star, precisely the way that Orge is mimicking the merging of two white dwarfs going to a massive white dwarf. And I think the afterglow there should be the same as the one Orge got for 17 or for 17, or foamy and black hole. But in that case, the inner engine works, and you have no final emission gravitational wave, but the formation of a fully spinning Kerr solution with the magnetic field. The trick is there: magnetic field present with Kerr, or magnetic field present with rotating, or a rotating neutron star. This is the key difference. All this blast wave and so forth, forget about. È chiaro?
Yeah, so at the end, in this way, you have the central engine. You may have the central engine with the black hole, spinning, and the magnetic field, which is fundamental for extraction through the electromagnetic critical field and so on. And still, you have the X-ray emission, then, which is on the other axis. Okay, thank you, Remo. Yeah, that's clear. Thank you.
È chiaro? Ok, c'è qualcosa da aggiungere? Rain, can you add something or what? Or you will hear?
I think for the moment, information was enough.
Tonight or otherwise tomorrow morning?
Yes, tomorrow morning
we
In any case, also tomorrow, no, we are here.
Yes,
Tomorrow morning
at 4
at 2 o'clock.
Yes.
Ok? Come andiamo?
Okay. Thank you. So thank you very much.
Any other question from the public? I can see.
Okay. So if not, I cannot share the screen. I always there. In the meanwhile, I thank again Remo and colleagues at ICRANET for inviting me for this discussion. Very, very useful for myself, for updating, and this is in the view also of better shaping the scientific case and requirements of next missions. So, okay, thank you. So I think you can see my screen. So of course, Remo and colleagues later on will mostly focus on the fundamental physics that we can address through gamma ray burst, as you heard. A very, very unique laboratory for fundamental physics of black hole and much more. So here in this, my general introduction, I just provide some clues to the other relevance of gamma ray burst for cosmology. For instance, the basic observational scenario, just to recap for all of you, what is the Amati peaky ISO relation. And also, I would like to provide to all of you the current scenario for next generation gamma ray burst mission, which is, as I said, one of the main aim, or the main aim is to fully exploit these events for fundamental physics and possibly also cosmology. So let me just go through the potentiality of gamma ray burst for cosmology. So here we are, of course, fully exploiting the huge luminosity of these events for index gamma rays, you know very well. This makes them detectable up to the very early universe. So we have these phenomena that can be detected from low redshift, so the, let's say, local universe, up to the first 100 million years after the Big Bang. So the epoch during which first galaxies and first stars were forming. And there are two main flavors of using gamma ray burst for cosmology, using them as tools for investigating the early universe, which I would say is thought to be by the gamma ray burst community the orthodox use of gamma ray burst for cosmology, which means using them for investigating, as I said, first galaxy, first stars, and cosmic ionization. But there is another very interesting potentiality of gamma ray burst that is instead to standardize them through the Amati relation and other correlations which are linked to this correlation for measuring cosmological parameters and hopefully getting some alternative cosmological models or dark energy and so on. So for the early universe science with gamma ray burst, as is sketched here on the right, this is putting gamma ray burst, long gamma ray burst in context, in a cosmological context. As I mentioned, this arrow shows very well how gamma ray burst can cover all the cosmic history. Moreover, as we know, at least a fraction of them is associated to the core collapse of very massive stars, as just discussed by Professor Ruffini in binary system in this case. So just to be very quick, the impressive thing about this is that it is true that there are nowadays some few very bright galaxies detected at very early universe, so a few 100 million years after the Big Bang, which means redshift higher than 6 than 7. But here, as you say in this picture on the bottom left, this is the fading infrared afterglow of the farthest away gamma ray burst. This is a gamma ray burst exploded at a redshift of 9.2, and what you see here is the fading infrared light following the burst, and this is a direct detection. So while it is true, again, that we can detect through the Hubble Space Telescope, the JWST, hopefully, or the LT, very bright galaxies, these very bright galaxies in the very universe are only the tip of the iceberg. The gamma ray bursts are a unique tool to detect directly the exploding star, in a sense, but as I showed here, this is even more impressive. If we point a very sensitive telescope like the HAC, the Hubble Space Telescope, to the direction of the 6 farthest away gamma ray burst, which you see here, actually after a few weeks or a month, when this fading afterwards that you see on the top left faded away, after that you can see nothing. So you know that in this direction, at this redshift, you have very redshift galaxies, likely small, low luminosity galaxies, only because you were capable to detect and localize the gamma ray burst with a good accuracy enough to have an efficient follow-up with robotic and then large telescope on the ground, catch this fading optical inner infrared afterglow and do absorption spectroscopy, and so learn where and at what redshift are the host galaxies of this gamma ray burst. This means that gamma ray burst provide nowadays and will provide in the future, even during the JWST and the LT epoch, a unique tool for unveiling the bulk of the population of primordial galaxies, which are small, low luminosity, and likely host the bulk of the star formation in the early universe. Of these invisible galaxies that we can detect only through gamma ray burst, not only we know that they exist, where they are, but through absorption spectroscopy of the fading afterglow, if we are quick enough to point a very sensitive telescope, we can learn the absorption through the absorption spectrum, the metallicity, the neutral hydrogen fraction through the Lyman alpha solution, and also the properties of the intergalactic medium. Again, these are fundamental information for understanding the metallicity evolution in the early universe, the evolution of cosmic ionization, but also to test if actually stars, primordial stars, and the ultraviolet photons produced by first stars can really explain the cosmic ionization, which is still a main issue in modern cosmology. So this high potentiality of gamma ray bursts for investigating the early universe are very well known by cosmologists. The issue here is that despite more than 25 years of effort by the main space missions or ground facilities, we are still stuck with only 5, 6, 7 gamma ray bursts at higher than 6. This is because of the inefficiency of current gamma ray burst detectors in detecting and localizing very redshift gamma ray burst, and the inefficiency introduced in the follow-up system. So you need the follow-up by robotic telescope on the ground, by large telescopes, and so on. And all this introduces huge inefficiencies. And filling this gap here is one of the main aims of next generation gamma ray burst missions. So this is a very clear and very important science case for gamma ray burst for next generation missions. And now I focus on the other side that I mentioned, which is instead using gamma ray burst for investigating the expansion rate and geometry of the universe, which means cosmological parameters, dark energy properties, and so on. So why, first of all, we should look for more cosmological probes. We have, of course, the subtype supernovae, the CMB, the combination of these telling us that the universe is almost flat and that the omega matter is around 0.3, which means that we are living in an expanding universe. But of course, as you can see on this diagram, the contours that you can derive, for instance, in the omega lambda plane from different probes have different orientation because they have different sensitivities to the cosmological parameters because of the redshift distribution and because of the different methods that are used for deriving cosmological parameters from these probes. In addition, each probe is affected by possible underestimated systematics. As you know, this is one of the main points that was made for the famous tension on the Hubble constant. If it is actually true, the tension between local, let's say, low redshift indicators like Taccone supernovae and the CMB, or this is telling us something important on fundamental physics and cosmology. For instance, Taccone supernovae, which you know very well, are the probes that first provided evidence of omega m lower than 1, and thus of the accelerated expansion of the universe, may be affected by different systematics that are summarized here. In the law, the famous correlation between peak magnitude and the shape of the light curve, which is used to standardize Taccone supernovae, which, as gamma ray bursts, are not standard candles, but can be standardized through this correlation. So the final aim is, of course, not to further confirm that omega m is 0.3 or 0.29, 0.31. The main aim is at the end exploiting gamma ray burst and all the other combined probes with future observation to assessing actually the properties and evolution of the so-called dark energy, to understand what is this lambda, the cosmological constant, or even to test alternative cosmological models. So let's go to gamma ray burst. Again, gamma ray burst show this huge redshift distribution up to 9.3 or even more possibly. So much beyond Taccone supernovae, much beyond baryonic acoustic oscillations, much beyond what Euclid, for instance, will do with ledge scale structure and galaxy distribution. Unfortunately, as you can see, very well known also this on the bottom right, the isotropic equivalent radiated energy or luminosity spans several orders of magnitude. They are not standard candles. As said, also Taccone supernovae are not standard candles, but very promising and very much investigated for standardizing gamma ray burst is, so now I take the occasion for introducing the peaky isocorrelation called Amati relation because of our first work, Amati et al. In 2002. You know very well that typically, not all and not during some part of the emission, but typically gamma ray bursts show a new spectrum which peaks at a photon energy, which is called peak energy, which may range from 10 keV more or less to thousands of keV, typically, can be even higher or even lower. And what we discovered, so clearly, this spectral peak energy is a key parameters of the prompt emission and is key for testing the many models that have been proposed for explaining the prompt emission physics. So we will learn more from Gorge and colleagues here at ICRANET. So what was found based on the first sample of Beppo-sized gamma ray bursts with measured redshift, as you know, the first redshift measurements of gamma ray bursts were thanks to the first measurements done by Beppo-Sachs, which allowed the first localization, the discovery of the afterglow, and then the follow-up with our telescopes and the measurement of the redshift. There was already a hint of this correlation between the spectral peak energy and the isotopic released energy, which was confirmed by later experiments, as you show here, while this diagram populates with passing the years, and with measurements coming from many different gamma ray burst detectors. So there was a long-standing debate. While this correlation is commonly accepted by the worldwide community, there were correctly some groups working on the possible selection effects or instrumental effects. The fact that the correlation holds, even if you take measurements by very different detectors with different sensitivity, different energy band, already is telling us that if there are selection on instrumental effects, these are marginal. This correlation is a power law correlation, or in log-logs, a linear correlation between log spectral peak energy and log released energy, which has a slope of more or less 0.5, and is characterized by a scatter, so a dispersion of the points along the best fit, which exceeds the Poissonian fluctuation, which means that there is an intrinsic dispersion, which is also a parameter of the correlation. So if you want to really characterize this correlation, you have to use a likelihood function or a model which is characterized by a normalization, a slope, and an intrinsic dispersion. All of these parameters are telling us something important on the physics of this gamma ray burst. And this is to show what I mentioned before. Different colors refer to different instruments. All these instruments measure the same correlation, which is really a strong evidence that no relevant selection effects are operating here. Very important is also to take into account that if instead of the radiated energy you use the peak luminosity, or usually referred as L-ISO, but this is a peak luminosity, which is, this is the same. This is indicating not physically the same, of course. The message is that the spectral peak energy is correlated with the brightness of the gamma ray burst. But if you want to go deep in this investigation, you have to take into account that the same correlation holds between spectral peak energy and radiated energy, and spectral peak energy and peak luminosity. Not completely surprising, given that, as you can see here, the radiated energy and the peak luminosity in gamma ray burst are very much correlated. So not surprising that the spectral peak energy correlates with both. Very important, and also I think very useful for investigators of the origin and the physics behind this correlation, is that if you do the time resolved spectral analysis, so you divide gamma ray burst like curve in several intervals based on the morphology or on the statistics, and you do the spectrum of each of these time intervals, and you compute the average luminosity and the spectral peak energy of each interval, you find what is here on the left, that there is any peak luminosity or a flux luminosity correlation, which is mostly the same in all within single gamma ray burst. So while here this plot refer each point is a different gamma ray burst, here on the left each diagram is a gamma ray burst, and each point is a time interval of that gamma ray burst. So this is telling us, and then if you measure the redshift and you put all these points of all these different gamma ray bursts all together, they follow all together the same peak luminosity correlation. So this means that you have a main emission mechanism that is operating through most gamma ray bursts that produces this correlation between, so a power correlation with a slope around 0.5 that produces at the end this correlation. Okay, I think this is a very important, a very summary of the observational scenario. Yeah, this again, yes, this is very important. So we measure, first of all, when we have an peak ISO correlation or a peak luminosity correlation for each gamma ray. So if we take different gamma ray bursts, okay, we do the time average spectral analysis, let's say. If we do the time resolved spectral analysis, let me go back, sorry, here, as you did many times in your fundamental works, you find that in most gamma ray bursts, for most or a majority of the duration of the gamma ray burst, the single points, so the peak, the spectral peak energy of each interval and the luminosity of each interval, you build a diagram. Each square here is a diagram of a gamma ray burst. Each point in a diagram is a time interval. You find mostly any peak luminosity correlation, which is the same slope as the peak ISO or peak luminosity correlation that you obtain considering the world events. So this is a clear. Yeah, you are building up. This is
precisely what
yeah.
Can show you.
Yeah.
Now the key point is go back to the one that you do. Yes.
Yeah.
Yes. The key point is try to understand this peak, each peak as a meaning. We fully agree that whatever peak you take, you come out with an Amati relation. But because there is a peak, therefore, since this is, of course, it will be displaced. Each will be displaced with the other one, but there will be always an Amati relation. Its character, each peak will have its own Amati relation. But
indeed, then this produces the scatter, the
Exactly.
dispersion. This is the message. That not all the phases of the gamma burst are the same or follow the same correlation. But for
But
most,
they are some.
yeah.
And the point is to understand physics, what they represent. On this point, we fully agree, and we fully agree. But the key point is, assuming, let's back to the assuming that each peak has, these are two different sources, and assuming that each peak has its own Amati relation, we have to look the reason of what is this double peak, what is the first peak and the second, the third peak. Second is, if you go to different gamma ray bursts, will you have different peaks? Or you will find, again, two peaks, or like in that case, 5 peaks. Which one fade away and which one stay? And this is, I think, something important, which gives the spread of that relation.
Yeah.
In other words, will we find the privilege peak? The privilege peak in which the relation will be just a line.
Exactly.
It's clear?
This is, as you said, So this,
Are you there? Are you there, Raim? You agree? Raim, can you intervene?
Yes, yes.
Raim,
Can you hear me?
it's clear. This is the key point. We fully agree on this.
Hello? Can I have a questions?
Yes?
now please.
Can I have questions?
Yes, please. Yes.
Okay. In this plot, a nice correlation plot, I want to understand how this information of depending on redshift Z. How can I figure out? Because you have so many events, but however, you didn't indicate the redshift number. How do I see that some information coded inside this correlation plot? In the other word, I try to understand you try to use GRB as a standard candle for cosmology. So
Yeah.
that's why I try to understand that plot code information of Z.
Yeah, I'm coming to that in a while. Yes, this was just to introduce.
But I wanted to.
Thank you for the question. I come to this.
Go back to, because you will speak about this tomorrow. Raim, are you listening, Raim? Are you there?
Yes. Yes, I'm here. Can you hear me?
Yes.
You agree that this is one of the key points.
Exactly. And I was thinking this relation that we can find for, it has been found for time-resolved spectral analysis. If we do it with more attentively, can support our idea of this self-similar structure of GRBs that we are looking for.
Yes, but this is still another question.
Yeah.
But the role of the supernova eyes, the role of the neutron star eyes, this is what really we are trying to do to see the water diagram that Lorenzo just showed. Okay, the further diagram, yes.
Sorry.
Yes, that one. Okay. Okay.
Okay, so yeah, thank you for this preliminary discussion. Yes, as said, many investigations on what this correlation is in these different forms, not different aspects of this correlation, can tell us about the fundamental physics behind gamma ray burst and gamma ray burst prompt emission. So this was already to mention, so there were already several attempts within the standard scenario and preliminary works. Non stavo condividendo. Adesso. Okay, sorry. And we were not seeing my screen, so now you see it. So as said, many works exploited this correlation or used this correlation to test and compare what the expectation in different scenarios between different assumptions in different flavor of the standard emission. There were also preliminary works, I would say, by the ICRNet gamma ray burst group, but let's continue this discussion later, no? That Remo already introduced, so I do not go further on this. Of course, the PK isoplane also is telling us something on the different origin and possible physics of the different subclasses of gamma ray burst. And again, this, as you can see here, with classical long gamma ray burst, let's say, following the correlation with this dispersion that is likely generated by the different phases of emission and so on.
Ray, can you please prepare to show at the end the Muccino plot with the different Amati relation for the short, let's say, flash, and so forth?
Yeah.
Yes.
Yes, thank you. So as you see, and as you know, because you worked on this, of course, just to recap, different classes of gamma ray burst show different properties, let's say in the PK isoplane. This is very important, including the very peculiar gamma ray burst 980425, which is the which is the so-called prototype of the gamma ray burst supernova connection, but is of a very a particular gamma ray burst.
You don't think in case there are three orders of magnitude energy missing.
Yeah.
You should think that.
What?
That there are three orders of magnitude of energy missing.
For this event, yeah. Yeah, no, the main interpretation in the standard scenario are that it is maybe a classical event seen very much of axis. No, you know, there are this. No, in the, let's say, the most common explanation within the standard interpretation is that it is a collimated gamma ray burst, very nearby as it is. It is the nearest gamma ray burst, long gamma ray burst, seen very much of axis. So you see it under luminous, it goes out from the correlation because of Doppler effect, let's say, the relativistic Doppler viewing effect. But of course, there may be different explanation. No, this is a standard. Yeah.
Sympathetic with
yeah.
High gamma. Because one thing we have learned is that all the GRB are low gamma. In
Yes.
And this jet at the sun is a profession which you would like to follow.
Let me ask you,
Please.
Yes.
From the statistical point of view, how many of 98 or 425 we should see if we assess the axis?
It's a good question. We did some simulation. Oh, ciao Luca. Hello. So
Chiediamo a qualcuno dei volontari di fare un caffè, così di mettere una.
So actually, if you accept that these are collimated events, no, let's say 10 degrees collimation jet, if you are so nearby, because this is a 0.00, it is much more likely to see it off axis. It is the same interpretation as the 1708-17. So if it is so close nearby, if it is actually collimated, it is much more likely to see it as an off axis event. No? It's very, so it's much more likely. Yeah. Yeah, no, you compute you put together the co-moving volume as that redshift, as a function of redshift, and assume a given collimation and the viewing angle. And
so my question is why we see when we have only 1%?
Yeah, but this is actually much more nearby than all other gamma ray bursts. So yeah. Oh, I'm not saying that this is the explanation. This is an explanation that has been put forward. But clearly, as you say, this is an important fact, no, to be explained by any scenario of gamma ray burst. Again, in the standard scenario, of course, as mentioned, this correlation is telling us something on the jet structure and the viewing angle, but I don't stop here. And now I go to because we will get back to the discussion on the physics of the correlation later on. No? We just discussed it preliminary with Remo and colleagues. So this is for the cosmology, and we have now Luca, who is also working, ciao Luca, welcome, on the use of these correlations for cosmology. So to answer the question by Shu, yes, we have a correlation between two quantities. One is the spectral peak energy, which is an observable, which is independent of cosmology. You simply take the measured spectral peak energy and you multiply by 1 plus z to get the cosmological restraint. But you have the other quantity, which is ISO, or the luminosity, which is linked to the observed fluence or peak flux through the cosmology, through the luminosity distance. So we are talking about a luminosity distance indicator, and inside the luminosity distance, there is the cosmology. So if you actually add enough low redshift gamma ray burst to calibrate the correlation in a regime where the cosmological expansion effects are negligible, you would have a direct tool to standardize gamma ray burst, very same way of type 1a supernovae. Instead, all or most of the gamma ray bursts used for the correlation lie at redshift higher than 0.1. So you don't have actually a determination of the correlation in a cosmologically independent way. Otherwise, you have the so-called circularity problem. So what you do is that, of course, is to fit all together the correlation and the cosmological parameters. So in other words, first of all, what we did with Massimo Della Valle and Filippo Frontera, very seminal, let's say, seminal work in 2008, he said, what happens if we change the value of omega m, which we use to compute the ISO? So we assume omega m 0, we compute the ISO for all the gamma ray bursts, and we compute the peak ISO correlation, and we do the fit, we measure the likelihood. Then we use omega m 0.1, then 0.2, and do the same up to omega m of 1. What happens? So would we detect a sensitivity to omega m? What I'm saying is simply to fitting all together in a flat, let's say, universe, the parameters of the correlation and the cosmological parameter. The only free cosmological parameter is omega n. And actually, what we find, I think this is really a beautiful and clean result, without taking any golden or platinum or silver sample. We took all the gamma ray bursts for which we have a spectral measurement and a redshift. We do this exercise, and what we find is that either you use the chi-square or use the minus log likelihood. The chi-square or the minus likelihood, so the goodness of fit has a nice parabolic shape as a function of omega m, and minimizes at omega m around 0.3, sorry. So if we could do this 25 years ago, before type 1a supernovae, this would have been a clear evidence that if the universe is flat, more or less flat as the CMB is telling us and the inflation predicts, let's say, we live in an accelerated universe because omega m is lower than 1. And this value of omega m is 0.3. So from one side, we have the confirmation that through this correlation, we can actually have a sensitivity to the cosmological parameter, and that they go in the same direction as the type 1a supernovae, the CMB, and the other cosmological probes. And this is in the same, as I mentioned before, this is a correlation which has an intrinsic dispersion. So this can be fitted, modeled with a likelihood developed specifically for this kind of correlation, which you have a linear correlation between the log-log quantities with an intrinsic dispersion. And through this likelihood, you can also measure, quantify the value of omega m, as you said. We could already in 2008 exclude omega m1 at almost 3 sigma confidence level, and this of course improved in the years I will show. And if you release the hypothesis, the assumption of a flat universe, you can also use 2 parameters, omega m and omega lambda. You could obtain already 10 years ago this kind of contour in the omega m and omega lambda planes that you can see is not much larger than what you obtain with type Ia supernova or cluster. This is quite old, I say. Nowadays, things are much better for all these probes. But this is to show how gamma ray bursts fit very well and in a very useful way in this, let's say, investigations of the cosmological parameters. This table shows the improvement on the accuracy of measuring omega m with this method, with the increasing of gamma ray burst in the sample. Now we are more or less around 250. So we started with 70 gamma ray bursts in 2018. Now we have 250. And this is the kind of accuracy you can get. I mean, there are many lines of investigation on how to improve. First improvement is to improve substantially the size of the sample. The fact, by the way, is that the accuracy improves significantly with increasing the size of the sample means that we are not still dominated by systematics in this analysis. The second part of the table, the bottom part, show for the same size of the sample, the accuracy you can obtain if you can calibrate the correlation. How can you calibrate the correlation? There are many works on this. You can use type Ia supernovae up to ratio of 1.4 and use those gamma ray bursts up to ratio 1.4 to calibrate. In this way, you are no more independent on type Ia supernovae, but you extend the double diagram for type Ia supernovae. You can find a number, 20, 30 gamma ray bursts in a very small bin or redshift. And again, you can see the correlation in this bin because I have all the same redshift, and so you have a cosmological independent calibration and so on. If you can do this, combining the enlarging of the sample and the calibration methods, you in perspective will be able to constrain, as you see here, the red contour, the parameters, for instance, of the dark energy in this classical modelization, parameterization, the CPL parameterization, where W0 is the current density of dark energy and WA is the evolutionary parameter. So very impressive. Much better in perspective than type Ia supernovae and barometric acoustic oscillation because of the much broader distribution in redshift of the gamma ray burst. Even if the transition redshift between dark energy dominated and non-dominated universe, having this is low, is around 0.5, 0.7, having a redshift distribution up to 9 in the double diagram allows very much to constrain also the shape of the double diagram at very low redshift. Luca, correct me if I'm wrong, but I think you are an expert. So we have already had an introduction on the fundamental physics that can be done with gamma ray burst as a laboratory. I just summarized the relevance of gamma ray burst for cosmology. Now let's have a look at the future. So clearly, future gamma ray burst mission aim at full understanding of the gamma ray burst phenomenon. There are so many open issues still. Fully exploiting them for cosmology, for fundamental physics, and also, of course, provide the very large facilities of the future that are being built in the electromagnetic domain, JWST going to be launched, ELT, TMT, SKA, Athena, CTA, you know very well, covering all the electromagnetic domain, and gravitational wave or neutrino detectors, let's say, in the future. So these are the main objectives. Let's also have a look at what the main agencies like ESA, European Space Agency, or NASA, or JAXA, or Chinese are selecting. This is the Cosmic Vision program by ESA. These are the missions that have been selected. As you may know, in ESA, Cosmic Vision programs, there are small, medium, and large missions, which depend on the budget and hence on the size of the mission and the scientific capability. If you have a look, you see that there are, many of them are dedicated to exoplanets, to the exploration of the solar system, and what is the purpose of all these missions on exoplanet solar system? clearly the main cultural theme is the life in the universe. It's not that we want to understand Venus because we're curious. Yes, we are also curious, but the purpose is to use Venus as a laboratory to understand exoplanets and hence a bit of the universe. Of course, I don't agree with this use of, so I think that the exploration of the solar system is just to explore the solar system, because the only way to understand if there are habitable planets in the universe is to do spectroscopy of the atmosphere of the exoplanets and look for signatures of life in the atmosphere. Stop. You see also cosmology missions like Euclid, but also Athena was sold to ESA as a cosmology mission, and so on. So clearly, the resonant keywords are cosmology, fundamental physics, and life. And gamma ray bursts are very much resonant with this. We just discussing this. Fundamental physics, first of all, also cosmology, as I try to summarize, but also let's keep an eye to the relevance of gamma ray bursts for the development and survival of life in the universe. So these are the main themes at which next generation gamma ray burst mission are aiming at. And again, let's keep an eye also on this relevance, because agencies are very sensitive to the theme of life of the universe, as we have seen. So in the very next year, what we expect, the main mission will be SWAN, Chinese-French mission, which will improve with respect to the current scenario where we have the Fermi GRB monitor, the SWIFT path, and so on, in the measurement of the prompt emission. And this is, of course, of interest for our colleagues, for instance, at ICRANET, which do this beautiful job, no, that analysis on the Fermi GBM, but the detectors on board SWAN will be much better, much larger, and with a larger energy band. Let's keep in mind that the Fermi gamma ray burst monitor is a very small detector compared to this next generation gamma ray burst detector. There are also other possible missions of interest gamma ray burst. The measurement of polarization of the prompt emission is also very much promising. Okay, where I also mentioned the nanosatellite programs like Hermes that aim at putting in the space network of 100 of very small nanosatellites, let's say 30 per 30 centimeter, each one carrying a small gamma ray burst detector, with the aim of localizing through, say, triangulation of these 100 satellites gamma ray burst. These are very, very cheap programs. But the main gamma ray burst mission concepts that are being developed for the next decade or the end of this one, and the ones that will actually allow to do this substantial step forward in fundamental physics and cosmology with gamma ray burst, here I summarize some of them, are all based on the same concept. So Theseus, which as you may know was coordinated by Italy, an European effort, which was selected by ESA in 2018 for a phase A study of 3 years as candidate next M5 mission, is the most advanced study. As you know, at the end, ESA selected a mission to Venus, and I don't comment on this, but of course, this is a completely different, this is a strategical, not a science-based decision, but the fact is that this is nowadays the most advanced study. Other study involve IZ Gundam in Japan, and especially in the US, in the USA, the scenario is very interesting and fast evolving with missions of different size, like TAP, Transient Astrophysics Probe, or GAMBO Explorer, which is small, TAP is larger than TSUS. All aim at substantially reducing the selection effects, the limitation of current gamma ray burst detectors for detecting very ratio gamma ray burst, and reducing the inefficiencies in the follow-up. So I described TSUS, but the concept is the same for all the other missions that I mentioned, in the USA especially, to extend the capabilities in the detection and characterization of the prompt emission, so extending to the soft X-ray, expanding to the 10 or 20 MeV range, and carrying on board directly an infrared telescope, which, thanks to the fast viewing capability of the spacecraft, will be capable of catch immediately the fading near-infrared afterglow of the gamma ray burst, and in this way will improve substantially the number of gamma ray bursts detected and identified at redshift, and at the same time will provide hundreds per year measurements of redshift and characterization over a very broad energy band of the prompt emission and also the afterglow. Okay, I can skip this set of instruments of Theseus. This is just to show that this combination of soft X-ray monitor, hard X-ray monitor, near onboard near-infrared telescope and fast viewing will allow this kind of missions to detect and localize and characterize any class of gamma ray burst much better than is done nowadays. Here you can see in this spectral peak energy peak flux diagram, the blue dots here are the bulk of the population of very high redshift or very soft gamma ray burst that are below the detection threshold, for instance, of the Fermi GRB monitor. So these next generation gamma ray burst monitors that I'm talking about, especially for TCUs, but can be proposed for any other mission of the future, will allow to unveil the bulk of the population of the soft gamma ray burst. So not only high redshift, but also soft class, X-ray flashes, and so on, still keeping the sensitivity to extreme events like the short GRB 1708, 17A. Just to show the capability of a machine like TCUs for the high redshift, what you see on the right is a cosmic cone where the gray dots are the gamma ray burst with measured redshift. You can see only a few of them above a redshift of 6, so only a few of them in the first billion year of the universe. The same you can see on the left in a luminosity redshift plane, and this is what will be done by a machine like TCUs in only 3 years of operation. So take into account that this kind of mission can live 10 or 20 years. Quindi in only 3 years of operation, a machine like TCUs will do much better, would do 1.5 orders of magnitude better than all the space missions and ground observatories in the last 25 years. So here a huge step forward, and of course, this measurement will have great synergies. This will be a great service for all these other big observatories that have been built and have gamma ray burst, transients, cosmology, fundamental physics with gamma ray burst in their core science. Let me spend finally a few words on one of the 2 monitors that was proposed and studied for TCUs, which is the X gamma ray imaging spectrometer, the XGIS, which has been led by Italy. It's based on an Italian technology developed in Bologna with OHB Italy in Lombardy, in Milano, and with the help of Spain, Germany, Poland, and Denmark in Europe, because these are coded mass cameras which show really unprecedented properties for gamma ray burst monitors that I summarized here. If you have a look on the plot in the top right, you see the effective area as a function of energy. As I was discussing before with Remo, with Jorge, you see the red line, you compare the effective area and the energy band extension of this instrument compared to the Fermi GBM or to the Swift BAT. So it is much more sensitive. It will provide us much more photons with respect to the GBM and extends to much lower energy. So you will have several hundreds of square centimeter effective area down to 2 keV, when the Fermi GBM has a few square centimeter at 10 keV, and in general has a peak effective area of 100 square centimeter at most. So this has to be combined with a timing resolution, which is again much better, for instance, the Fermi GBM or the Swift BAT. We can go down to a few microseconds or even below. This means that you can do that time-resolved analysis that we were mentioning before, time-resolved spectral analysis. It is so fundamental for the physics, for understanding the black hole physics, the central engine physics, the different phases, the peak ISO and other related correlation. This will be a substantial improvement. Okay, this is to evidence that it will cover excellently both the low energy and the high energy domain. It could also, in principle, be improved to measure also some polarization for further investigating the physics. This is how the instrument works. Just I don't want to go into many details. It's a coded mass camera which allows the instrument to do images to this gamma ray burst better than 10 arc minutes. And this is the basic principle. This is based on the detection plane, coupling silicon wave detectors, which work from 2 keV to 30 keV, with crystal scintillator detectors, which work from 20 keV to 10 MeV. So you have a monolithic detector, pixelated, which can work from 2 keV to 10 MeV, and you can build as large area as you want. You can build even much larger area than this one. This has more or less each of the cameras. There were 2 cameras for this use has 1,000 square centimeter. You have to think that the GBM has 80, 90 square centimeter. So it is 10 times Each of these camera is 10 times a detector of the FMGBM, which match, of course, a standard energy band. This is how the detection module works, but I don't go into detail. Again, it is this instrument that actually provides the bulk of this capability of TCUs to detect and localize and characterize all the classes of gamma ray burst. These are examples of spectra. So this is, you can see on the right, comparison between a spectrum from the FMGBM and a spectrum from TCUs. So you can see the difference. How much you will be capable to characterize, for instance, the black body emission, possible feature, absorption, and so on. Really, if you want to, we can do, of course, collaborating and performing simulations, we can provide you with a response matrix, the background, and so on. You can check by yourself what you can do with the current, with the FMGBM, and what you will be able to do with such an unprecedented instrument. And this is just to make an example, the analysis that was done by this team, ICRANET collaboration, on GRB 1901-14C, on this fundamental event, which allowed to do so unprecedented step forward in the understanding of the physics of the central engine, of the black hole, and much more, through this very sensitive and detailed terms of analysis. This is an excellent, exceptional event, very bright. You could do this and for many more events with an instrument like the GIS. Because if you did this with a small instrument like the FMGBM, of course you can do much more with the GIS. And of course, I would like to mention, gamma ray burst can also be used to test Lorentz invariance in many, or most, or let's say all quantum gravity scenarios predict that there should be a Lorentz invariance violation. So there should be a delay in photons coming from a very far away source, like gamma ray burst star, a delay, so with harder, so more energetic photons arriving later, and this delay is proportional to the difference in energy between the photons and the distance. So you have this gamma ray burst, which can emit over several orders of magnitude, and can be detected up to very, very, very redshift. So in principle, gamma ray bursts are also very, and actually some investigation were done in this direction with the Fermi GBM and LAT, but here the main issue is that if you do not understand the physics of the prompt emission, you cannot use in a reliable way them, because you don't know if these photons, low and high energy, are produced at the same time, in the same phase, no, and so on. So this is clearly requires both an understanding of the physics of the prompt emission and also more sensitive instruments. Okay, here I remark that thanks to the phase A study of ESA and the efforts of the Italian scientists and industry, now we have a good maturity, technological maturity for this instrument. So it is very, very much good to try to propose, as we are doing, to find opportunity not only within ESA, but also US or China and so on. So I think that the Italian community should push for having this instrument on board future missions, also not only ESA, but discussing with the US, we are doing with US colleagues or Chinese colleagues or Japanese, and that ASI and ESA that all funded the study of phase A study of TCUs and of this instrument should also invest again and more on this instrument to further improve and to be ready. For instance, if one wants to find an opportunity in China, the timeline of Chinese mission is very short, and you need to have a very high technological readiness level of these instruments. I conclude just summarizing the international scenario about these gamma ray burst missions. So in ESA, as you may know, ESA just released a few months ago the Voyage 2050, which will be the next program after the Cosmic Vision. And for the very large class mission, the main theme is early universe is among the main theme, but it's not intended, seems, as the early universe I was talking about before, so cosmic ionization, early galaxies and so on, but mostly for science of the CMB, whereas several teams have been proposed for M class. So, but there is no clear message in favor of gamma ray burst or time domain astronomy, but there is also no clear recommendation. TCU's project is going on, as I already mentioned many times during this presentation, and we are thinking of proposing it again for the next call for a medium class mission by ESA that may be issued already in the next month. Let's see how the scenario in the other country develops, because especially in the US, the scenario is very hot, because in the US there have been just released the recommendation of the decadal survey, the so-called Astro 2020 program, on which the next next missions that will be done by NASA will be according to this recommendation. So there are two kinds of recommendations that concern gamma ray burst. One is that there is a general recommendation to pursue time domain astronomy, multi-messenger astrophysics through small, medium missions. And this seems to favor a mission like the Gamma one that is coordinated by University of Washington and the JPL, and has been proposed as a small mission, as a MIDEX, so a small medium probe. There is another group coordinated by the Goddard Space Flight Center that is TAP, as I mentioned, transitory probe, that is for a probe. So while the MIDEX Gamma is smaller than a Theseus, than a medium class of ESA, a probe is even larger than a large mission, is larger than Athena, for instance. It seems likely that NASA will go for an intermediate, so for a mission which would be more or less slightly larger than an M, introducing a new class of explorer. So we have to see. We are in constant contact with the US colleagues. In Japan, we have this IZ Gundam, which is a small Theseus, again, which is being proposed by the UNETOC with TAL collaboration since many years, but still is stuck at a pre-phase A study. And in China, you know, there is a much interest in gamma ray burst science. Successful mission include POR, JECAM. They will collaborate with France for SVOM. Einstein probe is also going to be launched in a couple of years. They are working on a second polarimetric mission. Here, the scenario in China is always complex. You have the Chinese Academy of Science, the Institute of Energy Physics, the Chinese National Space Agency, and it's never easy to understand the interaction between these agencies, and so how the scenario will evolve, but we are doing efforts on all these sides. So these are my concluding remarks, summarizing what I already stressed. So I think I can stop here with this overview. I hope it was useful. This was to provide you this update and summary of cosmology with gamma ray burst, fundamental physics. We are going to discuss deeper the Amati and the relative correlations, and the perspective and the actions that we should take for next generation of gamma ray burst mission. Thank you. Thank you. Thank you, Raimondo. Thank you. Of course,
Thank you, Lorenzo, very much. Do we have any questions? Please ask questions.
May I?
Yes, please, Orgia.
Hello, I have a question.
Yes, first Orgia, then Chishan, please.
What is the timing, the solution of the cell? Because you are increasing the case, you have to also improve the timing.
Yeah. No, I was a bit quick on this, sorry, because I didn't want to take too much time. But as I mentioned, especially the GIS instrument, no? On which this instrument on which I focused, we joins this unprecedented energy band from 2 keV to 10 eV, as you see, with an effective area much better compared to the GPM, because it is one of the main instruments now, with a timing resolution of a few microseconds. It can be pushed even a few microseconds, but it can be also 1 microsecond or slightly less. HXMT is lower because it is based on a different technology. It should be much lower. No, the Fermi GBM is much lower. Instead, one of the main characteristics of the technology which this is based, which is silicon deep detectors and crystal scintillators, is that both detectors have a timing resolution of the order of the microsecond. So this is why, I mean, you can do, if you imagine a bright event, you can do spectral timing analysis, really unprecedented. And you can build much larger. So we are talking here about 1,000 square centimeter for each camera. you can build it as larger as you wish until the resources available on the spacecraft allow you. Yeah. So there was another question.
Please.
Hello. So I see the good point for using GRB to study the cosmology is it is a wide distribution in the redshift. Okay.
Yeah.
Then I ask the questions. Have you used this to see the Hubble constant H0 tension between the local measurement, means lower redshift, and the CMB measure, large redshift?
Yeah,
this be to see, to examine this constraint or whatever, the H0 tension, which is the problem for cosmology.
No, you're right. This is a main problem in modern cosmology. With this method, these gamma ray bursts are insensitive to H0 with this method without calibrating, because this is a method that wants to extract information in a way independent on other probes. So it's not calibrated because we don't have low redshift gamma ray burst to calibrate. However, here we have also Luca Izzo, who did a lot of work on this, so I may also leave the floor for, if you wish, Luca, to comment on this. If we use other methods in which gamma ray bursts are calibrated with type 1a supernovae, or with a number of gamma ray bursts in a similar Bezoar redshift, something has been done, but I think that there is not still the sensitivity to discriminate between the two values of H0. But Luca, would you have a comment? Yeah, switch on, I turn off my...
Hey, hello everyone. The main problem with the gamma ray burst, mainly with the H0 tension, is that the tension rises using supernova 1A, thanks to the fact that supernovae are very nearby. Just an example, the CSP sample that was used in the Pantheon dataset includes supernovae in the redshift range between 0.02 and 0.08. And we have 1 or 2 gamma ray bursts that cover this redshift range. But the main acceleration of the universe is sensitive in this very, relatively small redshift interval. That for supernova people is very large redshift interval, but for GRB people it's not. Then gamma ray bursts can provide an estimate of H0, but with a very large uncertainty if compared with other probes such as like supernova 1A. But on the other hand, GRBs can be really good to trace the history of the universe at very high redshift where there are no other cosmological probes, unless we consider quasars or other kind of probes. But GRBs are the most accurate ones, at least up to redshift 8, 10. I hope that.
Yeah, if I use, I remember, if we use this method that I show, which is actually to fitting all together the parameters of the correlation and the omega m, for instance, the parameter, you are insensitive to H0, because here H0 is only a multiplicative factor if you don't have a calibration. So here, for this method, you are insensitive to H0. But Luca can, it's simply a constant that multiplies. So. But Luca did something instead, exploiting this lower redshift gamma ray burst.
Yeah, but if you look at the analysis that supernova people is doing on supernova 1A, they are not using exactly the same analytical formula that GRB cosmologists are using. For example, Adam Reed's colleagues generally use the expansion series of the distal luminosity distance, well, the Hubble law, the simple Hubble law, to constrain H0. While for GRB, we just use the standard formula for the luminosity distance. But the problem is that we do not have probes at the low redshift. We do not have good enough GRBs. The Pantheon sample, now, last Friday, it was published, the Pantheon Plus. It's composed of 2,000 supernova 1A. in a very small redshift range. We have 3-4 gamma ray bursts that satisfy the Amati relation in this redshift range. So just a statistical issue. And Lorenzo, may I ask you a question about the cosmological? You have shown a slide, about Theseus and cosmology, and you have shown a sort of Hubble diagram that can be obtained with Theseus and the other, yes, this one. If I look at the, let's say, 2005, 2020 GRD sample and the Theseus sample, I see that the two distribution peaks at different median values. I see this as a strong selection effect. So if we consider only the sample in the first 15 years, I conclude that, okay, if we use this sample, we are neglecting a large population of gamma ray bursts for our cosmological study. What do you, am I right, or maybe?
Let me say,
Lorenzo, we cannot hear you. Can you activate the microphone?
Okay, sorry. So I was saying, the current, so the past, let's say last 20 years, the red dots here are, of course, these measurements are biased against the high redshift gamma ray burst. Theseus will reduce substantially the bias in high redshift gamma ray burst, improving very much the rate, the number of gamma ray bursts that we can have. But it is optimized for high redshift gamma ray burst, so it carries on board a near-infrared detector. So it will not be capable of autonomously measure the redshift for lower than redshift gamma ray burst, but this will still come from the standard method, so the follow-up from the ground that are, so this is simply due to the fact that here we plot only those for which the redshift is measured on board by Theseus, okay? So this is why you have a higher median. For a fraction of them, you expect to get the measurements also from the ground. Yeah.
Non ho capito, com'è che determini il redshift?
So the redshift, yeah, is the main purpose is to improve substantially the number of gamma ray bursts identified and with measure redshift less than 6. This is the purpose. Yes. Because you want to use them for the early universe science case, no? So the infrared telescope on board is optimized for redshifted gamma ray bursts. So it can measure the Lyman alpha break and so on, the features in the spectrum that are above 0.7 micron, let's say from 0.7, 0.8 to 2. If you have a gamma ray burst that actually lower than 6 or 5, you cannot use this technique on board. You have to rely, for a fraction of them, you will measure some lines in the spectrum, because there was also spectroscopy mode, but you will recover the spectrum only for a fraction of them. Other redshift measurement may come from the follow-up from the ground, because in any way, the procedures that are going on today for measuring the redshift from the ground will go on. So you are simply, actually, if you have a look to this distribution at the end, the bottom panel, you see that you start to, I mean, the median is higher because you expect to improve much more with current, with respect to current detection, of course. But, yeah. Yeah.
Maybe it can solve.
Yeah, it can reduce, of course, substantially the selection biases. Yeah.
I have a question also. If
yes.
Regarding to this 2 microsecond, the timing, it's very interesting. But how it is different from the time-tagged event of Fermi GBM, which can be as precise as around 1 microsecond?
No, it is here what plays main role is the statistics, no? So yes, so sorry for it. So the technical capability, also the GBM is based on crystal scintillator, so it's just a matter of the electronics, no? The readout and the front-end electronics that have to be optimized. So this kind of resolution is intrinsic in the physics of the scintillator. But you have to combine this, of course, with effective area. So I mean that with such large effective area, you could go down to this, let's say, time resolution with still statistical counts in each bin. So this is, I think, the main difference. Otherwise, yeah, you can fully exploit, let's say, thanks to the larger effective area, you can fully exploit the timing resolution.
I see. Another thing is maybe a conceptual thing. Regarding to this for cosmology, also there are other sources, as Luca mentioned, quasars. They are richer in numbers and they are more than GRBs. What makes GRBs more valid to do these studies in the early universe?
Okay. No, actually, nowadays, some AGN can be detected up to ratios of 6 or even slightly more. But gamma ray burst, much larger population at ratios than 6 and 7 if we have this kind of machine. And especially, they do not suffer of the so-called proximity effect. Here, you don't have a huge system inside the galaxy, which, let's say, which is distorting, influencing through the feedback, the properties of the environment in the galaxy. No? So you have a very, very, very compact source in a very specific region of the galaxy. So you have a much more reliability in what you measure. For instance, if you want to measure as I showed at the very beginning, the metallicity and neutral hydrogen fraction of these very primordial galaxies, you have a much more reliable measurement from gamma ray burst. You don't need to correct for all these proximity effects in AGN. And especially if you go at ratios 7, 8, or 9, I think that this is very difficult to detect AGNs in this way. So this kind of measure, this kind of spectroscopy, you can which is much more reliable to infer that these are the average properties of the galaxy along the line of sight, of course, not, let's say, significantly affected by the gamma ray burst itself. Whereas for the AGN, this is, I understand, one of the main issues.
I see. Thank you.
Thank you. Please.
When you construct the time resolve Amati relation, how do you see the working?
Yeah, this is a good question. There are, let me take this figure very quickly. So you should do two kinds of behaviors. There are many works here. I also did some works not published with some students, which we should publish. You have half of the cases, let's say, or 60%, in which the peak tracks the light curve. So naturally, you have the spectral peak energy, the peak energy of the spectrum, tracks the light curve. So it goes, rises when the light curve rises, no? Reaches a peak when the light curve peaks, and so on. And you can see this, for instance, on the if you look on the second row, the first column, no, this 2083, you can see that here the correlation is very tight between peak energy. This means that the peak energy is tracking the flux, no. So if you plot here, don't tell, sorry, a panel with the light curve, and the bottom would be the spectral peak energy is a function of time, you would see the same behavior in a case like this. But as you can see, in other cases, the correlation is more dispersed, because in 40% at least of the cases, you don't see that there is always this tracking. In more or less 40% of the gamma ray burst at the beginning, in the first phase, let's say here, the peak energy does not start low and rises, but starts high and decreases. Then, let me see if you see the, yeah. No, tracking means that the peak energy does the same. In other cases, you see that the peak energy starts here and decreases a bit, and then here starts to track, to go up and down with the line curve. So you have clearly a phase in at least 40% of the gamma ray burst, a first phase in which the spectral peak energy is not correlated with the peak flux. And this clearly, when you do the average spectrum or you put all together here, creates is one of the components of this dispersion. No? Of this, if you see here in these diagrams, clearly these diagrams are not showing the time. So it will be much clearer if I don't have now a panel with the evolution of the spectral peak energy. But you can see very much in the literature that you have 60% or half of the cases in which the peak energy follows the same trend as the light curve, no? Rises and goes down as the count rate, as the flux. In other cases, it starts and it evolves independently of the light curve in the first part, and then starts to track the light curve in the second part. This is very well known effect. In the second part, so in the tail, let's say, the second episode, or in the tail, you have almost in all the cases a tracking between the spectral peak energy and the peak flux, or the flux and the count rate. And this reflects in this dispersion in these diagrams, no? The ones that I showed you before. So this one, where is it? So always in the second part, 90% or almost the cases, there is the tracking. If the peak energy, so if the light curve rises in the last part, let's say, peak energy rises, then peaks.
What do we do in the last part?
In the last episode, let's say in the second half of the, for instance, of the gamma ray burst, or in the tail. Let's consider the top one. No, you can imagine there is one pulse, then another pulse, and then a kind of exponential or power of decay.
Yes.
So there are some cases for a gamma ray burst like this in which the spectral peak energy follows the light curve from the beginning. So it starts low, then goes higher, no, peaks, goes down, peaks, and decays. Other cases in which it starts already high, the peak energy, and then starts to track the light curve, or in the last part of the event, only in the last phases, let's say. So I can provide you, of course, later on some diagrams of this. But always, almost always in the second part, so in the last fraction of the duration, let's say, in the second half, more or less, the peak energy tracks the light curves. So, and you have a better, of course, a better. So here, when you see some dispersion, it is mostly due to the fact that the points creating this dispersion are in the first part of the gamma ray burst, where the spectral peak energy not always follows the flux of the light curve. Maybe it's more difficult to say than to see. It's clear, no? So this is telling us, of course, that if there is a mechanism that is producing this correlation, it is not always at work, but it is mostly always at work in the second phase of the mission, something like this.
Perché?
Perché la parte prima stavo cercando di sono sporche.
Ma non capisco, just to understand.
Yeah.
When you speak about the second phase, okay, tell me in second,
It depends on the duration.
Just
I can tell you in fraction, in percent, let's say in the last 50% of the duration. So if it lasts 50 seconds, let's see 25.
You are going to see around, you are looking around 50 seconds.
No, yeah, I'm taking the spectral peak energy in each interval, and if I plot the spectral peak energy as a function of time, no, as a function of it. So I see in some cases that it starts. Let's say that in some cases this is the peak energy, no? So the flux starts to rise, peaks, goes down, peaks, and this is
Yes,
the
I
flat.
understand.
And the peak energy does the same in some cases. In other cases,
Yes.
the spectral peak energy, instead of starting low and do the same, starts here.
Yes, you told me already, but
Ah.
I want to understand when you speak that you keep following
Here, let's say, okay, from here it starts to go up and down like the light curve. So it starts, it's going here, it tracks here, and then goes up and down. This is seen in very many cases, that the peak energy starts very high, here, arrives here, and at this time, starts to go down, up and down like
I
the...
understand, but without...
There is no general rule, it's...
without having the time in the rest frame of the source, is very hard to...
Oh, no, of course.
How can I make this point?
Yeah, no,
I mean, if you... we can look at some examples, and you will see. I mean, you cannot keep tracking after the prompt radiation phase.
Yeah, I'm talking about the prompt here, only the prompt.
Yes, but the prompt lasts very short usually. Does not, well, we will have to.
I can look for the data and then show you some examples on some plots where you have the peak energy and so we can discuss.
Yes.
We can see also the time scale because
yes, we will show specifically some cases with whereas it would be good that one
all the parli test.
Yes. Okay, let's try to move on.
Okay.
Then.
Okay. So
my problem is that it is appropriate to look for the you have the definition of the prompt, and then you have all the part of the afterglow where the luminosity drops very much. To try to find the characterization of the tracking, the luminosity in the last part is irrelevant for the relation with respect to the ISO. I mean, the ISO mainly generated
this is also
the early part of the prompt.
This is also
and if you propagate later, you are much away from the total ISO. And therefore, this cannot give you anything.
Yeah, no. I mean,
just a noise.
Yeah. But if you take this, this case here, when if you start to track here,
I like always to work with respect to time.
No, this is time. On the extra, this is time. This is count flux. Let's say as a function of time.
Is time in the rest frame or in arrival time?
Okay, this is I think in the observer, but
okay,
it's just to show the morphology of the light curve. Yeah.
Yes, but
so here you are. If you start to have the peak flux relation here, you are still considering a large part. But you have to take real examples, not to talk about.
We will give you some examples.
Yeah.
Okay. Let's proceed with the organ, maybe.
Yeah.
Organ.
Okay, so thank you very much for the attention and for all the discussion. I leave the floor to you. Yeah. Thank you.
I would like to
Jorge, please share your screen and activate the microphone. We cannot see and hear you.
Okay, so we break for 10 minutes, coffee break.
Okay.
Thank you very much.
Let's start again.
Okay. Jorge, could you please share your screen and activate the microphone?
I see that Anna and Civitarese are in contact from Argentina. Muratov is from Kazakhstan. I was surprised to find Alcide Garates. Can you put your camera on, Alcides? Mimosa is present from Alcide. You have to turn the camera down because we see the mirror. Okay, good,
Yes.
good to see
Yes,
you.
I am here. Yes.
Soroush, I think, is there. Beautiful.
I'm here.
Mimosa,
Yes, I am here.
your camera. Raim, Orge. Okay, we start again. Yun Long, Zhang. Who is Yun Long? Oh, yes, Yun Long. We have to speak about the book, but I see incredible, and I am so happy to see Bob Williams. Bob, show. This is a real surprise. Bob. Hello, Bob. Bob Williams is on the line. And this is a very, very nice surprise. Okay, we will hear as soon as he appears again. Jorge, let's proceed. Everybody. Dove sono? Amati and Lorenzo, dove siete? They stop in the coffee place. Call a moment. Wangyu. Wangyu. Call Lorenzo a moment.
Lorenzo.
So, is everything okay with you? We are waiting for.
Okay. Oh, yes.
Can we start again? Lorenzo and Caizzo are here. Okay, let's have.
I think.
Let's have a presentation.
Yes. Great.
By Jorge.
Okay, thank you. Sorry, let me just put this cable here, right here. So thank you. Great to see all these friends from all over the world following this discussion. So I try to be a bit general at some point to update all of you on what we have been doing on a very specific topic. Let me share the screen now. Oh, here we are. Okay, so speak about the GRB afterglows from binary driven hyperknowing and compact star binary mirrors. So as we should see, there are some properties which are shared by binary driven hypernova and compact star mirrors. So this will be more in the second part of this presentation. So we'll be a little bit mixed, but let me see if I can clarify myself this. So let's start. So we know the GRBs show an afterglow from low energy to very high energy. So here I'm asking all GRB, so all the supernova. So we have emission in the afterglow, so the emission after the prompt emission, from the radio to the optical to the X-rays, all the way to the GeV emission. So, but we are going to see a little bit what is the model we are following for the explanation of these two components that let's divide in two. One is the GeV, what is the GeV afterglow, and what is the other part, which is radio, optical, and X-rays. So these are two different components in our model. So this is the first thing to set here. So these are two different parts in our machine. So let's see the first about the GRB afterglow, which will show the role of the newborn black hole in binary-driven hypernova of type 1. So just to recall you, what is this? This would be just an example, just to clarify what we mean by this afterglow. So this is the example of the long GRB 190114C. So on the left, you see here is a different data. In the here is essentially from the X-rays to high energies, high energy to the up to the TeV emission. So you see here the GeV or GeV afterglow here, while the X-rays you see the black points here. So red is jet. That's right. Is the X-ray. So, and on the right, you will see it's more or less like the end of a movie. This will be, I will come back to this picture at the end of the presentation. Okay, this is the other components of the afterglow. You see here in the radio, this is the afterglow in the radio band, the afterglow in the optical, and the afterglow again, you see here red is the same as the black here, are the X-rays. As a special feature that you will see, that you see, but you see by eye, is the same power law behavior in time of the luminosity in the X-rays, optical, and radio. Right? This is the, these red points are the X-rays. Okay, that are the black points here. Well, I already said that. Okay.
There are two different parts you already said. First part, which is for the whole part. The second part is not evolution. But the two are connected. Certainly, through the fact that the extent of the globe continues the first part to the second part.
So, Rahim, I think, will speak tomorrow about the first part of about the prom emission, while I will be speaking here only about the after part. Okay? The part, all the emission following the prom phase here. So, especially the GeV emission and all the rest. So, this is just to show you an example of like your in the different wavelengths. Now I recall you the picture of the binary-driven hypernova, where you have the explosion of the supernova emission in presence of a neutron star companion in tight orbit. So you see here on the picture, this is the accreting, the neutron star companion accreting matter from the supernova explosion. And you can see here also, you see this is what we were calling the new neutron star, so the newborn neutron star out of the core collapse supernova. You see, it is also accreting matter from the supernova by fallback accretion, while this, but the accretion, actually the accretion on the neutron star companion it goes at much at higher rates, and it's actually the star which reaches the enough accretion to become a black hole is the neutron star companion. So here, along this process, you know, there is a lot of neutrino emission, which allows the neutron star to get to accrete at higher and higher rates, and at the end, after a few seconds, it can become a black hole by accretion. See also this asymmetry in the ejecta, in all this expelled matter. You see it becomes more and more asymmetric as time goes on. So and there is also a clean region here you see of low density, which is formed around the newborn black hole, and this will be essential in our picture. So what you will see, that you see I go after that. So we have, I go right away here to the point of the model of what is powering the GV afterglow in this model. So you see, you are forming this black hole out of the collapse, the gravitational collapse of the neutron star companion. Neutron star companion is for sure a magnetized object. So when this collapse from a black hole and is highly rotating, and actually during this numerical simulation, we follow the accretion of mass, but also the accretion of angular momentum. And so keep track of the evolution of the angular momentum of the star. And we can simply say, of course, that it will form a rotating black hole, of course. So a rotating black hole, and around this rotating black hole, we have the magnetic field, which was left by the neutron star, and we have also a region around this newborn black hole, in which we have an ionized low density, very low density matter around, which is left from the supernova ejecta, which of course it doesn't stop, for the matter continue to expand. So the density around the black hole, around all this region, continue to decrease with time. So we have essentially these ingredients, and these ingredients is what we call the inner engine of this machine. So this inner engine is the rotating black hole immersed in this magnetic field and immersed in this very low density ionized matter. But what this machine does? So there is when you have this rotating black hole, a curved black hole in a magnetic field, the spin of the black hole interacts with the spin with the dipole magnetic field, with the magnetic field, and it induces an electric field. Okay, so very much like a Faraday disc. So it induces this electric field by actually gravitomagnetic interaction. And these are the components. The components of this electric and magnetic field, as computed from the wall solution. Again, I forgot to change here. This is 1974, not 1074. And this is the solution for the electric and magnetic field around a curved black hole in an asymptotically aligned magnetic field that extends all the way to infinity. This is a detail, because actually what happened, what is important, what is really relevant in this system happens in the vicinity of the black hole horizon. So it doesn't matter if in this solution the magnetic field goes to infinity. So well, so we have this electric field, and of course, since we have ionized matter, if you have this electric field, it will accelerate particles, definitely. So let's see how this acceleration should happen. So what we see here are the electric and magnetic field lines around the black hole. So we have the black hole here, and you see the orange lines are the magnetic field lines, while the gray lines are the electric field lines induced by this system. In the case where you have both the magnetic field and the spin and the black hole spin aligned. So in this case, they are all pointing in flat z direction, both of them. In that case, the electric field in this region, you see this cone region, is induced inward, the electric field. So here it's inward, while here This, let's call this region polar region, while in the equatorial region is outward. So what happened in this case, of course, if you have an electric field inward directly here, you will have a negatively charged particles as being accelerated outside. So outward, yeah, outward accelerated. So yes. This cone has a half semi-aperture angle of 6 degrees, roughly. Actually, it's something like 55, 56 degrees. This region here, and you have electrons being outwardly accelerated in all this region. But they are electrons, and we have the magnetic field. So the electrons, they doesn't go just radially here, because you have the magnetic field. So actually what happened is that the electrons are initially accelerated with some angle with respect to the magnetic field line, but they are, of course, after that, they will be forced to follow magnetic field lines. So they will follow making the helix, so making a spiraling around the magnetic field lines, emitting synchrotron radiation. Yes, this is equatorial. Yes, there is equatorial symmetry. So they have what you see in the northern hemisphere, the same you see in the southern hemisphere, but of course in the other direction. So here electrons go south, here electrons go north. And in the equator, you see. Mm-hmm. Yes. That's correct. So here is a way to see this. Is you see this electric field? It has actually a quadrupolar nature. So you see the electric field lines changing direction, right? So you see these different patches. So this is as to like to have a positive and negative charge distributed in this way on the black hole horizon. Actually, the net charge of the system is 0. There is no charge here. It is just an induced electric field. But you can understand like as the black hole with a surface charge, with some part is negative and some part is positive. So that's why in some region you have electric field lines entering, while in other side you have going outside. Yes, but it's actually the opposite. You will have negative here and positive here. But anyway, then at the end, if you make the sum, you can see, right? You can see from here, from this, that this actually the charge is exactly the same. When you integrate over the horizon, where it is negative, where it is positive, they just have the same quantity but plus and minus sign. So the net charge is 0. So this machine accelerates charged particles. So we start to see what these relevant quantities that allows us to make astrophysical predictions for this system. So here, this is just the electromagnetic field energetics. Actually, this is the electric energy available. This is the electric field, which is accelerating particles. So we are interested in knowing how much energy, electric energy we have. So we can make a simple estimate actually, and we get this nice formula. This is just so it's proportional to the square of the magnetic field strength and this and to the square of the angular momentum of the black hole, and inverse proportional to the mass of the black hole. The maximum particle energy, the maximum that energy that a particle which is accelerated can reach is given by this very simple formula. This A, I remember, I recall you, this is just the angular, the specific angular momentum of the black hole. So this is J over M, and this is the magnetic field. Actually, well, it is this quantity is just the difference in the electric potential energy from the horizon to infinity. So this is the maximum energy that a particle can have. If you go to compute this quantity for the numbers we usually have in the black holes that are formed in GRB, so we have stellar masses, and this A over M of the order of 0.3, 0.4, 0.5, you will get that this energy is of the order of 10 to the 18 electron volts. So this is the maximum energy that a particle can attain. Of course, you have losses, you have radiation. So a particle which is accelerated cannot attain such an energy unless you don't have any loss of energy. And this is attainable only along the polar axis. Along the polar axis, so along theta equals 0 axis, you have the electric field and magnetic field completely aligned. Okay? And under such conditions, you don't have pitch angle for the particle when they are accelerated. Okay? So you reduce the losses by synchrotron radiation or any other. So essentially, along the polar axis, the particle can actually gain the highest possible energy. But in any other region of axis, the particles will radiate synchrotron radiation. And this process takes the energy at the end of the day from the black hole energy. That's why I am writing here the extractable energy from the black hole. So which is the amount of energy that we can extract from the black hole. Because you see here the energy, of course, the particles are getting the energy from the electric energy, which is available from that. But the electric energy comes from at the end from the rotational energy of the black hole, because the electric field is induced by the rotation of the black hole. So when the particles are getting infinity or radiate energy to infinity, at the end the energy of the black hole have to be reduced by the same amount in this mechanism. But
But can I ask a question? Huh? So you mentioned that electric fields are aligned with magnetic fields.
Only on the polar axis. Only along the polar axis. Look, only along this axis here. In any other place, it makes an angle with the magnetic field. No, it's the same. It's the same. It's the same field because the electric field is essentially radial. Okay, so along the polar axis is vertical, but in any other direction is not vertical, and the magnetic field is vertical by definition, because that is imposed to be in flat Z. Okay. So you have the magnetic field pointing in the Z direction, and then the electric field which is induced is nearly radial. So along the polar axis, they are aligned, the electric and the magnetic field. So that's why on the polar axis you don't expect that the particles emit any radiation, so they get just acceleration. Because to emit synchrotron radiation, you need an initial, yes. But now I show you the acceleration process. The particles actually they lose their energy in a very short distance, very short time. So it doesn't matter if the magnetic field bends after. It's not relevant. It's clear or not, or you have any doubt here? It's okay? So just to show you briefly, these are the equation of motion of charged particles in the these systems, including the feedback from radiation. So then you get to integrate those equations, and it's not important the specific one. They don't have the here. This is to show you this is the path that follow, for example, an electron near the black hole. So you see how this it follows this spiral emitting synchrotron radiation, and at the end it follows the magnetic field line. So this is essentially what will happen in this system. And while this is actually very short distance and very short time around the magnetic field. Actually, it's of the order of 10 to the, I will show in a moment, of the order of 10 to minus 14 seconds. It radiates all its energy, the electron. So let's see, this is the gamma factor. So you can see here, this is if you put an electron at different places around the black hole. So these are 3 cases. So these are for this is theta is 1 degree, 14 degrees, and 27 degrees from the polar axis. Okay. So I see here actually you see the gamma factor that you are reaching is of the order of 10 to the 4. Okay. So it means that the electrons have energy of half MeV, the rest mass that you have MeV. So actually by 10 to the 4, so you have essentially 10 to the 10 electron volts. Okay, so of the order of 10 GeV. This is the energy of electron, but all this energy is not transferred to the photons. Actually, to the radiation that is emitted. Actually, you see here on the right, this is the right is the energy, the characteristic radiation frequency, characteristic radiation energy. As a function of this is proper time. Okay, actually this is a extremely short time. So another feature that you see here is that you see the asymptotic Lorentz factor. This is because the balance between radiation and acceleration. So at the end you get an asymptotic value. So the particle cannot keep increasing the Lorentz factor because it is radiating. So this is the feedback from radiation. And you see that this machine emits naturally in the GeV region. You see the peak of the photon energy is typically for in the GeV radiation. That's why this machine is special to explain specifically that component. So since a synchrotron radiation, you see which jump to here. You see this is the spectrum. The spectrum of synchrotron radiation peaks near that characteristic energy. So it is a very few energy is emitted at different energies from the GeV. So this kind of system cannot explain you what you see, for example, in the X-rays or any other wavelength. So while it's special to explain the emission in the GeV regime, cannot explain the other part of the afterglow, which, as I will show in a moment, comes from another part of our system, from a different part. So this is the power emitted by a single electron. So then you multiply by the number of electrons that you have in the system, you can see actually that this system can explain of the order of 10 to the 51 air per second in GeV energies. This is what we expect from the numbers of our system. This is the characteristic time of emission. You see this what I was saying. This is of the order of 10 to the minus 14 seconds in very short time. Reach that scale. That is the radiation time scale, actually, synchrotron radiation time scale that gets at the end dominant. So they lose energy very fast, and this is actually why we can see high luminosity from this system. This is, it doesn't, okay, here it is. These are the numbers for the polar emission, but I already mentioned that. So they actually on the polar region, the electrons, the particle, the electrons can reach up to 10 to the 18 electron volts without losing that energy radiating. We have a power of the order of 10 to the 42 per second. These numbers are for typical stellar solar mass black hole, a spin of the order of half, 0.5, and magnetic field of the order of 10 to the 10 or 10 to the 11 Gauss. So we have also this particle, this very high energy means that this kind of system, these systems will have a contribution to the ultra high energy cosmic rays. How much? It depends on, of course, on the population of this system. One of the most important features of this system is that it can be scaled to the case of active galactic nuclei. By the end, you have a black hole in a magnetic field and with matter around. So it can be scaled to the case of active galactic nuclei. So this machine can work also for active galactic nuclei. You can just put, instead of 4 solar masses, you put 1 billion solar masses. And you scale the magnetic field, instead of 10 to the 11 Gauss, you put, let's say, 100 Gauss. Okay? And then you will get the numbers for an active galactic nucleus. So specifically in the part what is concerned cosmic rays, ultra high energy cosmic rays, that scalability of this machine can be very important for the explanation of ultra high energy cosmic rays. So what is your, excuse me, I didn't. You can have also proton acceleration, of course. 10 to the 21 electron volts.
Okay, so in principle, you can explain the TV emission of one electron, the other one proton.
Okay, with electrons you can't. But with proton it would be possible. But the problem is the following: that you have that you see, you have the 60 degrees on one side, and you can have only in that cone, you can have only electron acceleration, not proton. Proton will be on the other direction, on the equator. So if we are seeing this source, okay, from a privileged direction, okay, from a preferential direction, because you see that cone of 60 degrees, you cannot see the emission from the protons. So you cannot see both together. Okay? This is what I'm saying.
If you the speed and the magnetic position of the speed and the magnetic field, you in the polar and vice versa. If you have the magnetic field and the speed counter, you accelerate the photon and you need to do in principle, this is very interesting.
Now,
but it depends on the relative direction of the magnetic field.
And spin. Mm-hmm.
And it's not clear in the okay. Let's go.
So, yes. Yeah, this is true.
But you know, we talk about inclination angle of 60 degrees, but at the same time, gamma will become a factor of 10 to the 4. So one thing is the objective the angle, another thing could be
Completely different, because that beaming is of the single particle emission. But then you have particles being accelerated all over within that region.
and acceleration is homogeneous or
no, it can be all over, different direction.
Oh, but then along the polar direction, where the highest gamma acceleration.
Yes. Yes.
Okay.
Yes.
Yes.
Yes, because otherwise it would happen something. It would, if that would don't be that. Let me tell you, if you have electrons being accelerated in different directions randomly, then you will see you will have high energy photons going in different directions everywhere, and probably then you have the problem of photon-photon interaction that will probably get will dump the emission. Same.
But it's still apparently still a narrow condition. Maybe I think that you should do some simulation. And well, one thing in the rest free, but another thing is what we are observing. So I was wondering if the observed cognition generated blah blah is only due to a relative of this geometrical configuration. We should do some simulation. No, the collision angle is 60 degrees, but here I tell you the whole gamma factor, we have an arrow. Okay, the gamma factor is homogeneous distribution along the 60 degree angle, or there is a sort of distribution that peaks along the polar axis and then decreases.
Yes, I understand his point, but to answer that, we should run a simulation with a real, I mean, with many particles all over. That's very difficult. Yes, that's right. That's right.
Because we know already we see and that we will see. Because you will see the jet only if you submit the 60 degree. Then you can check how many you will see. And that you see the same.
So this plot, I don't know if this clarifies, but this is in the region where all photons that are emitted with energies of the order of GeV emission. Okay? This is from synchrotron radiation. So this is the roughly 60 degrees that you see. So the contours, these contours are contours of constant pitch angle, and I'm plotting here only the ones that lead to GeV emission. In the table, which plasma? It's not mine. It's not mine. It's the Earth. It's not me. This is Lorenzo. Good. M87, yes. These are the typical parameters of the machine. This is mass, spin, magnetic field, This is characteristic time scale of acceleration in the polar axis. This is the maximum electrostatic energy. This is the per particle. This is per particle, while this is the total electric energy available for acceleration. This is the power, so how many particles are accelerated per unit time along the pole. This is the typical pitch angles of the electrons of axis. This characteristic time scale of synchrotron radiation of axis, and this is the typical GV luminosity of axis. This is this one. So here is this is of the order. This is 40 microsecond for G14C, while this is 0.7 days. 0.7 days. So a few hours, let's say. Few hours. Okay? For an AGN. For an AGN. Okay, and this is I think this is the final slide on the first part, which is just a summary of how this machine works. So you have how the GV, the luminosity that you observe actually comes from the black hole, and so at the end what you are doing is extracting mass and angular momentum from the black hole. So at the end, by looking, when we analyze some GeV afterglow, so what at the end we get from this analysis, so from looking at the luminosity of this system, we get the mass, the angular momentum, and the magnetic field of the mass and angular momentum of the black hole, and the strength of the magnetic field around the black hole. So these are the three parameters that we get by requiring that the energetics of the GeV emission is paid by the black hole, that the luminosity is paid by synchrotron radiation ongoing around this black hole, and by requesting that since the photons that are emitting the GeV regime are transparent, that the system is transparent to these GeV photons so that they can actually escape. So from these conditions, we get these parameters: mass, angular momentum, and magnetic field. So the parameters of the inner engine. So this is everything that I have to say about the GeV afterglow. And let me go to this last part about the X-rays, optical, and radio afterglow. So here we will make some focus on the role of the newborn compact star. So we have on one side in the VDHN we have from the black hole.
Okay.
This is one problem.
Now we start talking that you have never seen yet. You have never seen yet.
Yes, the same. Yes, the problem that will be shown by exactly different.
But now we have to flash the alternative because now we change topics. Okay? Now you tell well, you just continue and we have the different phenomena. The X-ray optical spectroscopy, which are generated by a newborn compact star. Okay? These emissions can be originated in very different situations. The newborn compact star could be a massive white dwarf. But the same thing look at comes from a neutron star. A neutron star spin and generate again now, what object has been working tremendously hard now years has been to understand if you have a rotation while in the late fields, with the optical detail but tomorrow we are using the same machine, not working, but the Newton star. And one is the Newton star rotating in the median channel. This is not, it's a different one. But what is the median channel? The Newton star rotating. This will be the fantastic data which we will share to all range and light one. What we will show you in the recursion of flip source. What the magnetic what the sequence of radiation we need to do. Let's see down the white dwarf. What happens in the white dwarf? And then you can see
Actually, I will keep the first slide general, so you can see already that it applies to different cases. So this, in fact, the first question I'll try to answer is: there is common physical ingredient both in binary-driven hypernovae and in compact star mergers. So the answer actually can be found here. This is an example of a binary merger. This is taken from a simulation, of our article 2 years ago. So you see these are two merging white dwarfs. At the end, what you get the formation of a new object at the center. See, this new object at the center, in the case of a white dwarf binary merger, can be a new, more massive white dwarf, or there can be three different fates of this system. Of course, it can explode as a time 1A supernova following just double the generate channel. Okay, it can form a more massive white dwarf, or it can form a neutron star if the white dwarf, the same new central white dwarf collapses, gravitational collapse. But this is not relevant. This is relevant that you form a new object. In our case, I will assume here a newborn massive white dwarf spinning fast. It has been already shown that this system also has large magnetic field. Okay. These massive, fast spinning white dwarfs from this system. They have also high magnetic fields of up to the order of 10 to the 10 gauss. No, this not. Well, these properties from the white dwarf, actually, you can find this kind of system in different systems. We propose them, for example, as an explanation of soft gamma repeaters and anomalous X-ray pulsars, this kind that are the magnetars. Okay, so we propose this system for them, but you have them also in the double degenerate channel of type 1A supernova. In the case, maybe even a sort of novae, but I have not worked on that side of this. So this the system that you essentially you form a white dwarf that behave very much like a neutron star pulsar. So whatever you imagine that happens in neutron star pulsar, it may happen also here. What will be especially relevant for this discussion is that you see from the simulation that is matter that is expelled also. So you see, you form a newborn object at the center, rapidly spinning. You have a magnetic field which is large, and you have matter which is expanding around. And actually, what you see, this is essentially, this is actually, you see here, these are cuts from the simulation, and you see this is the matter expanding around the object. So what is you see, you can you can already establish what these commonalities, these common properties of this system. If you have a BDHN, you have a neutron star merger, or a white dwarf merger. You have but it's the same thing that happened. You have expelled matter in these systems with a new central object for center. So in the case of a BDHN, we have the new born neutron star at the center of the core collapse supernova. The matter that is expanding is the matter of the supernova explosion. In the neutron star merger and in white dwarf merger, you have the matter that is just get unbound during the merger, which expands, and you have a newborn object. In the case of a neutron star merger, it can be a black hole, or it can be a more massive neutron star. In the case of white dwarf, it can be a more massive white dwarf or a neutron star with a gravitationally collapse. A few numbers, you see, the mass in the case of a white dwarf merger, which is a spells of the order of 10 to minus 3 solar masses, and is similar to the amount of mass in a neutron star, neutron star merger. The magnetic field, this is important. The magnetic field that you expect, we are interested in the transient at the beginning of the post-merger life of the system. When this, it means that the matter which is being expelled, which is expanding around, is tracking still the magnetic field, which is the magnetic field of the central object. This is different if you want to see the behavior of this when this expanding matter is very far away. In that case, you have to go to a treatment like a pulsar with nebula, which is very different from this. So when you are close to the object, then you have the behavior that you expect from the magnetic field of the object. Specifically, we are in the region where the most important field that we expect is the one of that toroidal component of the field, which decays as 1 over r. This is very well known from pulsars, and we are assumed like it is something like 1 over r. And there is an injection of energy from the central object. In the case of the neutron star merger, you have also an interior source of energy of the ejecta, which comes from the decay of our process, nuclear. While in the white dwarf merger, you don't expect that. So you have a source of energy from the center, but not from inside. And it's not dominant. What is the mechanism for emission that we are interested? So it's again synchrotron radiation, but not synchrotron radiation as we were discussing before, but you have here just expanding material in the magnetized medium that is given by the central object because it was highly magnetized. It's highly magnetized. So you have again synchrotron radiation going on in this system. And then you have an energy injection from the central object. So to compute that synchrotron radiation from that, you have to solve this equation that is down there in the kinetic equation for an energy injection. So essentially what you have here, you have to compute the evolution of the distribution of electrons in this system by knowing how it expands. How it expands is given by this alpha. Now I will give this. How this emits. This goes from here, that is synchrotron radiation, and here what is the injection of energy. So it's an energy balance equation. So these are the ingredients. So we will assume some profile for the density of this inside the ejecta. So you, of course, you have some law, which will assume as it was a 1 over r to the m. Okay, so that you can explore different possibilities. But say 1 over r power law in the radius, I will assume as a similar expansion. So that's why you see this evolution of the density as t to minus 3 n. This n is because here we will assume that in general the evolution is not we will not assume from the beginning that it's just a uniform expansion. So it can be also accelerated expansion. That can be measured by this index n. Okay, so you have the energy injection from the central object. We will assume in this way. So a power law, we will assume a power law both in energy and in time. So here we have also a power law in time. And the magnetic field you see here is 1 over r. So it changes as 1 over r. But since this can be accelerated at the end, it can decay with time as 1 over n. So it's not that the magnetic field is decaying itself, but it's just the front which is expanding. The shell that is expanding is seeing a magnetic field which is slower as it expands. So you can solve this equation that this is the solution. You can find a general solution from the energy, the evolution of the energy of a single electron which is going inside, is losing energy because from expansion and from synchrotron radiation. You can get this general solution from that. Then you get, you can put in this general solution of the kinetic equation, and you can find this approximate law. I will not go into the details, but I just want to point out that you will get, if you put power law minus gamma into minus gamma, then you get it increasing by unity here at the end of this process. And you have also power law in time. So I will show, this is the contribution from the pulsar behind. So you have at the center the new object that it behaves like a pulsar. So these are equations of a typical pulsar emission, but we are including also the quadrupole component of the possibility of a quadrupolar component in the magnetic field. So you have a little bit, something a little bit more complex like the typical pulsar. The treatment in textbooks, but you have this will allows you, and we have indications already that this quadrupolar component is needed from the afterglow of GRB, because the typical pulsar, when you have only a dipole radiation, the luminosity, the pulsar luminosity decays as t to the -2. So it goes like time to -2. But we know from GRB afterglow, actually, that the luminosity goes asymptotically to an index something like -1.3 or something similar. So it doesn't follow the pure dipole component. Any pulsar, there is no pulsar that follows the pure dipole picture. So the GRBs are not deception. So let me go to a specific example. Now I will show this is a famous source, 1708, 17A. This is one of the most beautiful sources to analyze from this point of view, from the point of view of the amount of data that we have. This is a famous source because it was, you remember, this was the very loudly announcement of the neutron-star merger from LIGO. And there is the multi-wavelength data also at longer times, which is now giving us a lot of information. I remember to the people here that actually we soon after the publication, the first announcement of this source, by comparing this source with the typical short GRBs sources that we knew at the time, we immediately identified that this system was very different from any neutron-star merger. And so we proposed at the time that actually it was what looks more similar, like possibly a white dwarf merger. So that was our initial proposal, and that we follow in two papers. One was essentially observational, and a second paper which was theoretical, in which we were computed what would be the observables of such a white dwarf merger. And actually what we are doing now is the extension of that work. Actually, we are computing more and more in this emission in more and more details. And we have now more data of this source to compare treatment. So these are X-rays, you see, this is X-rays, these are optical, and this is the radio emission from this source. And the solid curve are, of course, is the fit of the data by this treatment. I will show now some views of this, but you see that the fit is very good. The fit of the data is extremely good. Well, let me go here. Yes, maybe you see here, this is the radio, optical, and X-rays. What is very important to emphasize here is that from the beginning you see that was the rising of the light cube in the X-rays and the optical and in the radio was roughly the same. I mean, it's the same slope. Then it reaches the peak at the same time. Then it starts to follow with the same slope again, the three. And this was, for us, typical of this emission dominated by the synchrotron radiation, this same slope in the three bands. Then what is new now, that you see, that you expect from the synchrotron radiation, that they keep to follow that slope. But then we know that in the X-rays, the X-ray emission started to deviate, starts to depart from that power law behavior, but not the optical and the radio. And this actually was, we predicted that in a paper of 2 years ago. We predicted that because we expected the emergence of the white dwarf pulsar. And actually, in our paper, we predicted that this, maybe I should show the paper, that when we show the emergence, actually, that we were expecting something like this. So this is the emission from the pulsar that you see around this time. And it causes this deviation from here. So you expect the optical, radio, and the lower energy bands to keep decreasing as the synchrotron, while the X-rays are show the emergence of the central object. The emission from the central object becoming transparent. Let me, well, then of course you have this the emission of this, an additional emission from this system is the thermal cooling, not only synchrotron cooling, but also thermal cooling, because of essentially of the expansion. Because this system, as you saw in the previous slide, the emission was absorbed at the beginning, and this you see because you see the rising of the emission. So the energy was absorbed at the beginning. So you have the central source which injects energy, and this energy enters into the system from the bottom layer. These layers emit synchrotron radiation. Okay, but this synchrotron radiation is not immediately transparent because you have all this density, you have all these shells of matter ahead of this. So this energy, part of this energy is absorbed and hits the matter. And this heating is then released bit by bit during the expansion. Okay, this causes an extra component. Your cocoon, the cocoon. That's right. That's right. This is like the cocoon. So you have this energy. Okay, so you have this energy of that is keep released bit by bit by thermal cooling. So this is this was one of our simulations in the 2019 paper, but now let me show you one of the latest. Oh, sorry, this is some evolution.
But you just a point before you go ahead. You mentioned that at the beginning the source was absorbed.
Mm-hmm.
What do you mean?
No, you have this energy which is injected from the bottom layers. Then the synchrotron radiation acts. That's fast. So synchrotron radiation is emitted, but you have an extended. You have extended matter. Yes, it's optically thick. Also from the observation point of view, because in this yes, it was absorbed. In all bands, it was absorbed. No, you have this.
In the beginning, well, in the first day, you not have this.
Ah, no. Oh, but it keeps optically thick for more than that. In all of them. In all of them. No, yes, but look. The blue.
27 corresponds.
Okay, you're right. Not in the optical, but in the radio, yes, you see that. In the optical is not as clear as in the radio. Okay, the optical is not as clear as in the radio. That point you are right.
In that you are missing
some data.
Because the source, was detected.
Yes, this is
after the
yes. I know. That emission is here.
But one day is
that emission. That emission is here. No, that emission is here. I'm not sure. I'm showing only here the synchrotron. Okay. Yes, it's not missing. It's here. Is this one? This is the data you say. That is before 10 to the 5 seconds. Okay. That is what we we explain as the thermal cooling, not as a synchrotron. Okay. Because it was partly absorbed, it was partially absorbed and then re-emitted as it expands. Okay, so part of it is emitted as cooling. Okay, but at this time, so this is not synchrotron. This is just the photospheric emission. So actually, you can derive to do that. You have to you take the data, you have to divide it in many shells, okay, and follow the evolution of all these shells separately, and then to estimate where the evolution of the transparency from, and compute make estimate of this. This is of course an approximate treatment. You have some specific assumptions, okay, but it seems to work relatively well. Not completely. You see, for example, this emission is not cached by the system, okay, but this is the emission in the K-band, but because the model is extremely simple, okay, it has some assumptions, it has some gray opacity, so not depending on the energy. There are, but possibly more important simplification that we have here is the asymmetry, and we are assuming a spherically symmetric expansion, while possibly there is asymmetric expansion of the ejecta. So we should include some velocity dependent on the latitude. So this is probably the most important effect that we are neglecting here, that we think that as soon as you include that, you can catch much better the thing. But broadly speaking, the model works very well in explaining the data. This is the case of 019. This is just moving ahead from a different case. This is 190114C. But all this probably not the best example. Okay, probably one is probably better than 180720B. But also here you see the possibility of again you see these same slopes going in the X-rays, in the optical, and in the radio, which are a sign of essentially a sign of synchrotron radiation going on. And also you have here the contribution. This is green line contribution from in this case the new object at the center is the new neutron star from the collapse here, because this is not why the merger. This is a BDH 1. Again, you see here some the possible contribution, the contribution from it to explain the late time after. So, sorry. No, this is last slide. This is the last slide. Stop here. Red says red. Well, I used to read the legend. So No, let me tell you one thing, okay? Because you are requesting me to make a change of all the plots inside a visual for a presentation in which in the middle of an Everest work of every day. That I can handle to do that. No, not in the future. I can do that. So I take, because the pictures are taken from different works, and I cannot keep adapting every picture to keep homogeneity in the presentation.
Questa è una fiducia. Va bene? E quando tu guardi, questo è il canale del
No, di fatto
By magic. That cannot be explained by synchrony.
ma non entriamo nelle stesse immagini però qua diciamo per quale dello stesso fenomeno allo stesso tempo dello conflitto un po'
Questa è forse una delle differenze certe da
macchina
esatto.
una stile di
Questo
spiega
ci sono due possibilità.
che spiega tutto l'Excel Assembly, cioè quando tu lo porti quello che sei
Okay, fine. But now I have a question who are all the time. We can have a whiteboard and then to start spinning and making with radiation. But there is an observational way to distinguish between the two machines. And it's related with one question that you need to Lorenzo about the time resolution of the instrument. Because you know the time scale of the emission is related directly with the dimension of the emission. So if you be 170817, you do not see millisecond in the scale emission. If you see millisecond times the emission, probably you can exclude.
Yes, I didn't speak about the parameters, but you're right. In this case, in our simulation, the white dwarf has a rotation period of the order of 12 seconds.
No, independently of the rotation period, the light travel time. You're talking about the light travel time. There are time variation, the emission time, which is very low, maybe a fraction, maybe I don't know, issue computation. You can compute directly the dimension, the size of the emitting source.
But you need, for Jeremy 170817, you don't have the statistics before. So big, no?
Yeah, because we don't have the statistics. I think
this is what we need an instrument like that. No, it's exactly the.
But if you can go to the resolution, time resolution, necessary to constrain the emitting source, you will have directly an answer to your model. Because you can have a dimension of the emitting source.
Dimensions are different. Because, I mean, you can make the same treatment similar, okay, for the case of a Newton star merge, Newton star binary merge.
I completely understand. But from maybe now our observation I'm looking for some observational evidence that can confirm or exclude or reject one of the models. I think that this is the best observational proof evidence that can confirm or exclude one of the models. But we do not have the detail.
The question is what would be such time scale? What is the expected to discriminate?
Well, if you observe time scale, I don't know what now the numbers, but if you see variation of order of inside the not less, I think you can exclude the whiteboard. Then now, they also large now after in the formula.
But the person, but from which data you mean?
No, you don't have enough statistics. But what is
From the afterglow, you mean? In the afterglow? The afterglow.
But what is the original?
I don't see the problem.
In the case of 1708, prompt emission volumes.
The prompt of 17 is it has a luminosity, a peak luminosity of 10 to the 47 per second, but just half a second. It's worse than 10 to the
Sort of breakout, a sort of shock breakout, because there is a thermal.
there is a thermal dominant. It's dominant. It's dominant in this case.
It's dominant, but not only thermal, but
there is no non-thermal. There is also non-thermal.
We are
Because you have to point that the short gamma data to do with the normal event is not similar to all the shots that we have from 20 years or not completely. And this is something that makes me wonder. Something that makes me wonder how can it be different, and other people say, okay, we have observed the jet below.
Exactly. This Cristiano Guidozzi asked me. So in the typical picture, people explain the very large difference in energetics, but assuming that you are seeing this, but that is question of a line of sight, okay, of axis or whatever. What is your explanation? So our explanation is this is a different system. This is a different system. So this is not the same extrapolating a parameter.
It's true that if you want to take that system, the only way is to make an argument about the energetic of the system.
If you explain that the prompt emission is shock breakout from emerging of 2 hours ago,
look, we didn't make a model for the prompt, okay? Okay. But let me tell you something about the prompt. Because here it is. Yes, that's Fermi GPM.
What was like the 19? So what kind of like in the bonus line in the PGM later, in the PGM don't find
worse.
They mentioned that in half of the pattern from the emission they found that they're not clear. I don't see. No.
It's not that we compute that. There is some.
We have one exact. We give exaggeration in text of the word. We expect
No, but you're right. There is a clear term.
Sometimes I saw they want to say to see a thermal component. The statistic is very difficult to distinguish between a thermal component or a part of power alone. So, if I can ask you a question I was asking to Jorge, is the time scale, no? So, for 17 and 17, you have Israel dancing 17. Here you have a few days, no?
No, these are seconds. These are hundreds of seconds.
Here you are affected so this is due to the different objectives.
Yeah, these are just different numbers of the different. These are completely different numbers. Different. You have different to get something like this. You have to main parameters defining these are the opacity. This is one the density profile are the main component. But essentially, what be the difference is that you have some synchrotron radiation ongoing. Also, not that everything is absorbed, but you have also produced ahead, and then you can see that from the very beginning. So, but in the other case, it's not like that. So you have
the different conditions. They also living to the different
different environment.
One of the weakest objects the weakness. Anywhere we found the physics is completely different. And also these curves are completely different. The only thing we are emphasizing is that the qualitative, the splitting thing between X, optical and radio, okay, is characteristic of synchrotron. Much weaker in one side, much harder in the other one. But this is our key message. Our key message is, if you like to put it more dramatically, okay, that if you are looking at the X-ray afterglow of a PDHM or of this system, there are three of them. X, optical, and radio. These people do not realize. And of course, the magnitude is completely different. But the fantastic thing of the presentation, which I followed with some difficulty, but I understood what he was planning, is that he has found a commonality between completely different systems fulfilling the same synchrotron radiation procedure. I already got this. And the important point, which will be stressed, which is already present, is that there is not one X-ray after when we go asymptotic. There are three after. And this is essential. We will show you why it's essential. Because somebody spoke with us who was not there. We were speaking with someone who said that you have to in this source, okay? In this source, the supernova, what is the supernova?
It's going to be Yes, I want to show that. I think it should be this bump here. No, no, this is optic.
Where did you take this stuff?
Which one?
No. I'm making this question because I have to take some of the data. I have okay, Andrea Melandi.
I would like to point out something. The light of the supernova is below the X-ray of that. How can you see that? If you the traditional idea is that the supernova is over the X-ray. That's the traditional illusions. That's okay. The supernova is below the X-ray. Yes, below. And the reason is trivial. If you take into account that they are trivial, it is over the optical. Not the T-point is not the X-ray. Okay, this is time to be interesting for you. We are classified. After the people in the literature would speak about after the ocean, the bullshit. C'est des différences. It works for such two different systems. You have to consider two extreme. Otherwise, I want to reach, if you want to reach and explain to you what works. But you have to what do you tell the school? Okay, but we will show you. Okay, the key point is what also master. If you take anything, from the system, pushing something you used to what but later down, you reach transparency. And later down, or you discover something intelligent. That is so, and you know what? We have gained this understanding after fighting for 1 year, 2 years or 17. I mean, this, in order to prove that the meditation way we develop the analysis of that system, which gave us to understand the C'est d'accord.
Yes, I would like to also to mention this, the point of the thermal emission, the cooling, which Luca correctly pointed out that is very good, is the cocoon. Speaking about the cocoon, because out of this kind of treatment is clear how you can get or make. I show you the result of the other sources. Is of the other source that we start to analyze, or previous source that we analyze in some way, but when you look into this, 060218.
Abbiamo voluto capire di nuovo la situazione di ciò che avevamo identificato. È istruttivo, ma finalmente l'abbiamo capito. È chiaro che si dà sì, completamente altro. E questo è scoperto. Quello è per quello che questo c'è una volta 98 45.
È povero di dati, 980425.
Ci siamo no, c'è una segnatura nuova, ma lasciateci lavorare con calma, e non è chiediamo. Anche se il primo, questo è la cosa lo sa. Il primo scovato è quello più eccezionale di tutti. Secondo me, se vi devo dire la verità, uno potrei dire i dati questi, ma non è vero, cioè c'è in quei dati c'è una logica. Questo è il problema. Sì, cioè c'è una logica, cioè c'è una
Questo è vero.
Vabbè, credo che per oggi io mi scuso con il Gabriele, alle 4 va via 2 ore prima, va bene? Perché alle 4 vi spiegavo io alle 2 parto alle 2 domani. No. Però ho paura che anche uno rimane bloccato la tendenza delle cose. We should say I don't be attended.
Okay, yes, we see.
Would you like to say something to the
Okay, it was very interesting and enjoyable to follow all this discussion. Dear friends, it was really fantastic to follow this development. After many years, we are reaching the point of solving the Amati relation with a new understanding. But what is more important is that we are understanding all the details of GRBs, all the details. And it's revolutionary because it has details which we never expected And I thank you all for being with us. And I think we have to take a break. Tomorrow morning, let's say we will start again around 9 o'clock, 9:15. And have a good night. And I'd like to ask a moment to Angyu, Rahim, and Liang Li. Anna, did you follow, I hope? And I see always Bob Williams. I hope so much that he followed and appreciated the revolution going on.
Okay.
Bob.
Hi all.
Anna, fatti vedere, c'hai la camera?
Mi funziona la camera.
Ti vogliamo rivedere? Non ti si vede.
Domani mi collego dal tablet.
Va bene, a domani.
A domani.
Guarda che abbiamo capito tutto. Ciao. A presto. Dobbiamo solo scrivere.
Ok.
E riflettere anche sulla sorgente che tu avevi studiato.
Ok.
A presto, ciao.
A presto, ciao ciao.
Ok.